What if everything we know about being first is wrong? The assumption that humanity represents Earth's inaugural experiment with civilization runs so deep that we rarely question it. We measure our progress against stone tools and cave paintings, constructing a narrative where we stand alone at the pinnacle of 4 billion years of evolution. But this assumption rests on a foundation more fragile than most people realize. The geological record, which we trust to tell us the story of life on Earth, is not a comprehensive archive. It is a heavily edited manuscript with most pages missing, and the few that remain are often illegible. When scientists examine the preservation rate of fossils, they find that significantly less than 1% of all species that ever lived left any trace we can detect today. The vast majority simply vanished, their existence erased by the relentless processes that reshape our planet's surface. This raises an uncomfortable question that a small but growing number of researchers are beginning to ask seriously. If an industrial civilization existed on Earth, millions of years before humans, would we actually be able to find evidence of it? The question is not as absurd as it first sounds. Earth is 4.5 billion years old. Complex multicellular life has existed for over 600 million years. Humans, in our current form, have been here for perhaps 300,000 years, and we have had anything resembling industrial technology for less than 3 centuries. If we compress Earth's entire history into a single 24-hour day, all of human civilization occupies the last fraction of the final second before midnight. The scale is almost incomprehensible, and within that vast expanse of deep time, there are enormous gaps where our knowledge fades to nothing. Could something have risen and fallen in those blank spaces? The standard response from mainstream science has always been no, but that answer is changing. Not because new evidence has appeared, but because researchers are finally asking what evidence we should expect to find, and whether we have been looking in the right places at all. The conversation began in 2018 when astrophysicist Adam Frank and climatologist Gavin Schmidt published a paper that would force the scientific community to confront an uncomfortable gap in their understanding. They were not proposing that ancient civilizations actually existed. Instead, they were asking a more fundamental question. If one had existed tens of millions of years ago, what geological traces would remain, and would our current methods even detect them? The answer surprised them. They called their thought experiment the Silurian hypothesis, naming it after an episode of Doctor Who featuring an ancient reptilian civilization that predated humanity. The name was playful, but the science behind it was rigorous and deeply unsettling. What Frank and Schmidt discovered was not evidence of ancient aliens or lost continents, but rather a troubling void in scientific methodology. No one had ever seriously attempted to determine what markers a long-vanished industrial society would leave in the geological strata. The tools and techniques paleontologists use to study ancient life were designed to find bones and shells and the impressions of biological structures, not factories or circuit boards or the chemical residue of fossil fuel combustion. This realization opened a door that many scientists had assumed was permanently sealed. To understand why this question matters, you need to understand geological time and the processes that erase history. The Earth's surface is not static. Tectonic plates drift across the mantle, carrying continents with them. Mountains rise and erode away. Seafloors spread apart at mid-ocean ridges and disappear into subduction zones, where one plate slides beneath another, melting back into the mantle. This recycling process is extraordinarily efficient. The oldest seafloor anywhere on Earth is only about 200 million years old, which means that any evidence on the ocean bottom from before that time has been completely destroyed. Continental crust lasts longer because it is less dense and does not get subducted as easily, but even continents undergo constant transformation. Rivers carve through rock, glaciers grind down mountains, sediment accumulates in some places and gets stripped away in others. The landscape you see today is not the landscape that existed even 10 million years ago, let alone 100 million. Every feature is temporary when measured against the full span of geological time. Consider what would happen to our own civilization if humanity suddenly disappeared today. This is not idle speculation. Researchers who study this scenario, often in the context of understanding long-term nuclear waste disposal or environmental recovery, have constructed detailed models. In the first few decades, wooden structures would rot and collapse, steel and iron would rust, glass would shatter, concrete would crack as water seeped in and froze. Within a few centuries, most buildings would be reduced to rubble. Within a few thousand years, that rubble would be buried under sediment or broken down by chemical weathering. Plastics would persist longer, perhaps tens of thousands of years, but even they would eventually fragment into microplastics and then degrade further under ultraviolet radiation and microbial action. Radioactive materials would remain detectable the longest, their decay following predictable half-lives, but even these signatures would fade and disperse over millions of years. The key insight is that preservation requires very specific conditions. An object must be buried quickly, protected from oxygen and water, and situated in a location where geological activity will not destroy it. These conditions are rare. The fossil record provides a sobering example of how incomplete our window into the past actually is. Paleontologists estimate that we have discovered and catalogued fossils representing perhaps 1/10 of 1% of all species that have ever lived. The rest left nothing behind that we can find. Even among the species we do know about, our sample is incredibly biased. We find fossils primarily in sedimentary rocks that formed in environments where dead organisms could be buried quickly, such as river deltas, lake bottoms, and shallow seas. Creatures that lived in mountains or forests where erosion dominates over deposition are far less likely to be preserved. Soft-bodied organisms rarely fossilize at all unless exceptional conditions exist, like the Burgess Shale, where fine sediment and low oxygen levels allow delicate structures to leave impressions. When you account for all these factors, the picture becomes clear. The geological record is not a complete library of the Earth's history. It is a scattered collection of fragments, and the older the rock, the more fragmentary it becomes. Entire epochs might be represented by a single thin layer of sediment, or not represented at all. Now apply this same logic to the artifacts of civilization rather than biological organisms. A bone has certain advantages for preservation. It is made of mineral, primarily calcium phosphate, which is already chemically stable in many geological environments. It is often buried quickly after death if the animal dies in the right location. And crucially, bones exist in enormous quantities because every animal that ever lived had a skeleton. Even with all these advantages, fossilization is rare. Now consider a smartphone or a car or a concrete building. These objects exist in much smaller numbers than animal skeletons. They are made of materials that corrode or decompose relatively quickly on geological timescales, and they are typically located on the Earth's surface where erosion is active, not in depositional environments where burial might occur. The chances of any individual artifact surviving for millions of years approach zero. A steel beam might last thousands of years, but over millions it becomes iron oxide and disperses. Aluminum corrodes. Copper oxides dissolve. Even materials we think of as permanent have finite lifespans when exposed to water, oxygen, and geological activity. But Frank and Schmidt were not asking whether we might find an ancient smartphone buried in a rock layer. They were asking whether an industrial civilization leaves any signature at all, and whether that signature might persist in the geological record even after every physical artifact has vanished. The answer lies in chemistry. When a civilization burns fossil fuels, manufactures synthetic materials, mines metals, and reshapes landscapes, it does not just create objects. It alters the chemical composition of the environment in measurable ways. These alterations can be preserved in sediment layers, ice cores, and even the composition of rocks themselves. The question is whether these chemical fingerprints are distinct enough to be recognizable millions of years later, and whether they could be distinguished from natural processes that might produce similar signatures. This is where the analysis becomes genuinely interesting, because it forces scientists to think about what makes industrial activity unique from a geochemical perspective. What chemical changes occur during industrialization that cannot be easily explained by volcanism, meteor impacts, or other natural phenomena? And once those changes are identified, how long would they remain detectable? The answer lies in carbon isotopes, and the story they tell about how energy flows through Earth's systems. Carbon exists in two stable forms, carbon-12 and carbon-13. Both are chemically identical, but carbon-13 has one extra neutron, making it slightly heavier. This tiny difference creates measurable effects in biological and geological processes. When plants photosynthesize, they preferentially incorporate the lighter carbon-12 into their tissues, because it requires slightly less energy to process. Over millions of years, as dead plants get buried and transformed into coal, oil and natural gas, this preference becomes locked into the fossil fuels themselves. The carbon in these fuels is depleted in carbon-13 compared to the carbon in the atmosphere or ocean. When you burn fossil fuels, you release this depleted carbon back into the environment, and the ratio of carbon-13 to carbon-12 shifts in a measurable way. This shift gets recorded in the shells of marine organisms, in the organic matter that accumulates in lake beds, and in the carbonate minerals that precipitate from seawater. Geologists can drill sediment cores and measure these ratios layer by layer, constructing a timeline of how the carbon cycle has changed over millions of years. This technique is already used routinely to study ancient climate events, and what it reveals is both fascinating and troubling for anyone trying to distinguish industrial activity from natural processes. One of the most studied events is the Paleocene-Eocene thermal maximum, which occurred roughly 56 million years ago. During a span of perhaps a few thousand years, global temperatures spiked by 5 to 8 degrees Celsius. Ocean sediments from this period show a dramatic negative excursion in carbon isotope ratios, meaning a massive injection of carbon-13 depleted carbon flooded into the environment. The leading explanation involves the destabilization of methane hydrates on the seafloor. These are ice-like structures that trap methane molecules, and they form in cold, high-pressure conditions on continental margins. If ocean temperatures rise even slightly, or if sea levels drop and reduce the pressure, the hydrates become unstable and release their methane. Because this methane comes from decomposed organic matter, it carries the same depleted carbon-13 signature as fossil fuels. Once released, the methane oxidizes to carbon dioxide, warming the planet further and potentially triggering more hydrate release in a feedback loop. The isotopic signature of the Paleocene-Eocene thermal maximum looks remarkably similar to what our own industrial civilization is creating right now. If you examined a sediment core from 10 million years in the future and saw a thin layer with depleted carbon-13, elevated temperatures, ocean acidification markers, and changes in species distribution, you would have two competing hypotheses. Either a natural carbon release occurred, triggered by some combination of volcanism, orbital changes, and feedback mechanisms, or an industrial civilization burned enough fossil fuel to alter the global carbon cycle. Without additional evidence, distinguishing between these scenarios becomes nearly impossible. The chemistry is identical, the timescales can overlap. The only difference might be in the rate of change, because industrial combustion can release carbon much faster than most natural processes. But even this distinction becomes blurred over geological time. When you compress thousands of years into a few centimeters of sediment, rapid events start to look gradual, and the resolution needed to detect a difference vanishes. Frank and Schmidt recognized this problem and pushed their analysis further. They asked what combination of markers might be uniquely industrial, signatures that would be difficult to explain through purely natural processes. Synthetic materials emerged as the most promising candidate. Modern civilization produces hundreds of millions of tons of plastic every year. Polyethylene, polypropylene, polyvinyl chloride, polystyrene, and dozens of other polymers are manufactured from petroleum feedstocks and shaped into products that end up distributed across the entire planet. Much of this plastic eventually reaches the ocean, where it fragments into smaller and smaller pieces. Some of it sinks and gets buried in seafloor sediment. Over geological time, this buried plastic would be subjected to increasing heat and pressure as more sediment accumulated on top of it. The polymers would begin to break down, but they would not simply vanish. Instead, they would be transformed into a suite of organic compounds that do not occur naturally in significant concentrations. A geologist analysing ancient sedimentary rock might find anomalous concentrations of specific hydrocarbon chains, or unusual ratios of aromatic compounds, or synthetic additives like plasticizers and flame retardants that have no natural source. These would appear as chemical ghosts, the residue of materials that once existed in vast quantities but have been broken down and dispersed. The challenge is recognizing these signatures as artificial, rather than attributing them to some unusual natural process. Until very recently, no one was looking for such markers in ancient rocks, because the question had never been posed seriously. The analytical techniques exist. Mass spectrometry can identify organic compounds with extraordinary precision. Gas chromatography can separate complex mixtures into individual components. but these tools are only useful if the scientist operating them suspects that something unusual might be present and knows what to look for. Another class of potential markers involves trace elements and their distributions. Industrial mining concentrates specific metals in ways that natural geological processes rarely achieve. Copper, lead, zinc, tin, and other economically valuable elements get extracted from dispersed ores, refined to high purity, and then manufactured into products that eventually corrode and disperse again. But this secondary dispersion is different from the original geological distribution. It creates anomalies. Urban areas, manufacturing centres, and mining regions accumulate elevated concentrations of heavy metals in soils and sediments. These accumulations can persist for thousands of years, and in some cases they might leave detectable signatures in the rock record. The difficulty is that volcanism, hydrothermal activity, and meteor impacts also create metal anomalies. Distinguishing an ancient smelting operation from a hydrothermal vent requires context that may not be available in rocks millions of years old. Rare earth elements present a particularly interesting case. Modern technology depends heavily on elements like neodymium, dysprosium, and europium for electronics, magnets, and catalysts. These elements are extracted from specific ore deposits and concentrated in industrial products. When those products decay, the rare earth elements are released in patterns that differ from natural weathering and erosion. Some researchers have proposed that unusual rare earth element ratios in ancient sediments could serve as technosignatures, but this remains speculative. Natural processes can also fractionate rare earth elements through chemical weathering and precipitation, so any signal would need to be unambiguous and occur in association with other anomalies to be convincing. Nitrogen isotopes offer yet another potential marker. The industrial production of fertilizer through the Haber-Bosch process converts atmospheric nitrogen into ammonia, which then gets applied to agricultural fields. This artificially fixed nitrogen has a different isotopic composition than nitrogen fixed by bacteria in soil and root nodules. Over decades and centuries, agricultural runoff carries this nitrogen into rivers, lakes, and oceans, where it gets incorporated into sediments. A future geologist might detect an anomalous nitrogen isotope signal in sediments dating to the 20th and 21st centuries. But interpreting such a signal millions of years later would be complicated by the fact that natural nitrogen fixation rates have varied throughout Earth's history, influenced by factors like ocean chemistry, atmospheric composition, and the evolution of nitrogen-fixing organisms. The pattern that emerges from all these examples is consistent. Industrial activity leaves chemical fingerprints, but those fingerprints are often ambiguous. Natural processes can mimic them. The signatures degrade over time, and most importantly, they only become visible if someone is looking for them with the right tools and the right questions in mind. This realization leads to an unsettling conclusion. If an industrial civilization existed on Earth tens of millions of years ago, we might not recognize its traces even if we were staring directly at them. We might attribute anomalous chemical signals to volcanism or impact events. We might dismiss unusual isotope ratios as analytical errors or contamination. We might simply never look at the right rocks in the right way because we have no reason to suspect anything unusual. The absence of evidence in this context tells us very little about what actually happened in Earth's deep past. The problem becomes even more acute when you consider the dynamic nature of Earth's surface and how thoroughly it erases the past. Subduction zones consume oceanic crust at a rate of several square kilometers per year. Every piece of seafloor that existed more than 200 million years ago has been pulled down into the mantle and melted. This means that any evidence of civilizations that might have existed on continental margins or islands during that time has likely been destroyed. Continental crust survives longer, but it undergoes its own forms of recycling. Erosion strips away surface layers. Sediment buries old landscapes. Mountain building crumples and metamorphoses rock, destroying original structures and resetting chemical clocks. The oldest continental rocks on Earth date back 4 billion years, but these are rare exceptions. Most continental surface rock is much younger, and the older it gets, the more likely it is to have been altered beyond recognition. Consider the specific case of urban centres. A modern city concentrates materials and creates distinct chemical signatures in soil and groundwater. Concrete foundations, asphalt roads, metal pipes, and buried infrastructure all represent artificial structures that differ dramatically from natural geology. But cities are built on the surface, precisely where erosion is most active. If you want to preserve something in the geological record, the surface is the worst possible place for it. Sedimentary basins, where material accumulates and gets buried under successive layers, offer better preservation potential. But cities are rarely built in locations that will become sedimentary basins. They are built on rivers, coastlines, and strategic high ground, locations that are either eroding or stable, but not accumulating thick sequences of sediment. Over millions of years, a city would be worn down to nothing, its materials scattered and diluted beyond recognition. The only exception might be if a city happened to be buried rapidly by a volcanic eruption, like Pompeii, or by a massive landslide or flood deposit. Even then, the structure would need to avoid subsequent erosion and tectonic deformation, a combination of circumstances that becomes increasingly unlikely the further back in time you go. This raises a critical question about where we should look for evidence of ancient civilizations if we take the hypothesis seriously. The surface is too dynamic, the seafloor is too young, mountain ranges are too deformed. So what environments offer the best chance of preservation? Deep sedimentary basins in tectonically stable regions provide one possibility. Places like the Amazon Basin or the Congo Basin accumulate sediment steadily over millions of years without being disturbed by mountain building or subduction. Drill cores from these basins contain continuous records spanning tens of millions of years. If an industrial civilization had existed and left chemical signatures in the environment, those signatures might be preserved in these sediments. The challenge is that these basins are often remote, difficult to access, and have not been extensively cored for scientific purposes. Most drilling in sedimentary basins is done for oil and gas exploration, and the analysis focuses on finding hydrocarbons, not looking for anomalies that might indicate ancient civilizations. Caves and other underground voids present another intriguing possibility. Limestone caves form when slightly acidic groundwater dissolves carbonate rock, creating hollow spaces that can persist for millions of years if they remain below the water table or in dry conditions. Objects that fall or are placed into caves can be shielded from surface erosion and weathering. Paleontologists have found remarkably well-preserved fossils in cave deposits, including delicate bones and even soft tissue impressions in rare cases. If an ancient civilization had used caves for habitation, storage, or burial, artifacts might have survived there longer than anywhere else. But finding such caves and recognizing artificial objects within them presents enormous challenges. Most caves that existed millions of years ago have either collapsed, been filled with sediment, or been destroyed by subsequent geological activity. The caves we explore today are relatively young in geological terms, most having formed within the last few million years. Older cave systems are vanishingly rare and often completely altered. Another potential repository of evidence is impact craters. When a large meteor strikes Earth, it excavates a deep crater and can bury surface materials under layers of impact, melt, and breccia. These buried materials are then protected from erosion and can remain preserved for hundreds of millions of years. If an ancient civilization happened to occupy an area that was later hit by a meteor, some artifacts might be preserved in the impact deposits. However, the violence of the impact itself would destroy most structures and scatter materials chaotically. Moreover, large impact craters are rare, and finding one that both postdates a hypothetical ancient civilization and contains recognizable artifacts would be extraordinarily unlikely. Still, the possibility exists in principle, and it illustrates the kinds of unusual preservation scenarios that might be required to find physical evidence across deep time. The Moon offers a completely different preservation environment. It has no atmosphere, no water, no plate tectonics, and no life. Once something is placed on the lunar surface, it can remain essentially unchanged for billions of years, aside from gradual accumulation of micrometeorite impacts and cosmic ray damage. If an ancient Earth civilization had achieved spaceflight and left artifacts on the Moon, those artifacts might still be there, vastly better preserved than anything remaining on Earth itself. This idea sounds like science fiction, but it is scientifically sound. The Apollo landing sites remain essentially as they were left in the early 1970s, and they will remain recognizable for millions of years barring a direct meteor strike. If we found structures or objects on the Moon that predated human spaceflight, it would be unambiguous evidence of a previous technological civilization. several researchers have proposed systematic searches of lunar surface imagery for artificial structures, though no such program has been implemented comprehensively. The difficulty is that the Moon's surface area is enormous, nearly 38 million square kilometres, and analysing it all at the resolution needed to spot anomalies would require substantial computational resources and time. Mars and Venus present similar possibilities, but with different complications. Mars has a thin atmosphere and low geological activity, so surface features can persist for billions of years. The Viking landers, Pathfinder, and various rovers we have sent to Mars will remain recognisable for millions of years. If an ancient civilization had visited Mars, evidence might still exist on the surface. Venus is more problematic because of its extreme surface temperature and pressure, which destroy materials rapidly, and its volcanic resurfacing has obliterated most features older than a few hundred million years. Still, certain locations like the Highlands might preserve evidence longer. The point is that, looking beyond Earth to geologically stable bodies in the solar system might offer better chances of finding evidence of ancient technological activity than searching Earth's heavily recycled surface. This leads to a broader consideration of what we mean by evidence and how we recognise it. Archaeology trains us to identify artefacts as objects that show clear signs of intelligent design and manufacture. A stone tool is recognisable because it has been flaked in patterns that do not occur naturally. A pottery shard is recognisable because clay does not naturally form into vessels with uniform walls and decorative patterns. But these recognition criteria depend on the artefacts being relatively intact and retaining their diagnostic features. Over millions of years, a stone tool might weather until it becomes indistinguishable from naturally fractured rock. A metal object corrodes into oxide minerals that look like ordinary ore. The decay process does not just destroy the object, it destroys the very features that would allow us to recognise it as artificial. This creates a fundamental epistemological problem. We cannot find what we cannot recognise, and we may not be able to recognise artefacts that have been degraded beyond the threshold where clear design features remain visible. Chemical and isotopic signatures offer a way around this problem, because they do not depend on recognising individual objects. Instead, they look for statistical patterns in the distribution of elements and isotopes across layers of sediment or rock. These patterns can persist even after all physical structures have vanished. But as we have seen, interpreting these patterns is difficult because natural processes can create similar signatures. What is needed is a combination of multiple independent lines of evidence that together become difficult to explain through natural causes alone. A single anomaly can always be dismissed. Multiple anomalies occurring in the same time layer, especially if they represent different types of industrial activity, become progressively harder to attribute to coincidence. This principle of convergent evidence is well established in science. When multiple independent measurements point to the same conclusion, confidence increases dramatically. In the case of detecting ancient civilizations, you would want to see carbon isotope anomalies coinciding with elevated concentrations of synthetic organic compounds, unusual metal distributions, nitrogen isotope shifts, and perhaps radioisotope signatures, all appearing in the same narrow stratigraphic interval. The probability that all these anomalies would occur simultaneously by chance becomes vanishingly small. But assembling such a case requires comprehensive analysis of sediment cores, something that has not been done with this specific question in mind. Most geological studies focus on narrower questions, reconstructing past climates, understanding extinction events, mapping the evolution of ocean chemistry. The data that might reveal evidence of ancient civilizations could already exist in archived cores, waiting for someone to analyse it with the right perspective. The resolution of the geological record introduces another layer of complexity. When geologists talk about events happening at a specific time in the past, they're usually referring to time windows that span thousands or even millions of years. A thin layer of sediment that looks uniform might actually represent 10,000 years of deposition. Small variations within that time window get averaged out and become invisible. This matters enormously when trying to detect industrial civilizations, because the duration of industrial activity might be quite short compared to geological timescales. Human industrial civilization has existed for roughly 200 years so far. Even if it continues for another 1,000 years, that is still only 1,200 years total, a blink in geological time. If that entire period gets compressed into a sediment layer 1 millimeter thick, detecting the signal becomes extraordinarily difficult. The chemical anomalies would be present but diluted across the layer, potentially blurred by bioturbation, where burrowing organisms mix sediment, and complicated by diagenesis, where chemical reactions alter sediment composition after burial. The duration of an industrial civilization might also affect what signatures it leaves. A short-lived civilization that existed for only a few centuries might not burn enough fossil fuel to create a globally detectable carbon isotope anomaly. It might not produce enough plastic to leave a clear synthetic residue. It might not mine enough metal to create significant elemental anomalies. The detectability of a civilization scales with its longevity, energy consumption, and population size. A smaller civilization, or one that existed for a shorter time, would leave fainter traces that would be even harder to distinguish from background noise. This creates a detection bias. If ancient industrial civilizations existed, we would be more likely to find evidence of the largest and longest-lived ones, while smaller or more transient civilizations might remain forever invisible. The analogy to the fossil record is exact. We find fossils of abundant, long-lived species far more often than rare, short-lived ones. Energy consumption provides a useful metric for thinking about detectability. Modern industrial civilization consumes roughly 18 terawatts of power continuously, most of it from fossil fuels. This energy consumption drives our carbon emissions, our materials production, our mining operations, and essentially all the chemical signatures we leave in the environment. A civilization that consumed less energy would leave proportionally fainter signatures. But there is a threshold below which detection becomes effectively impossible. If an ancient civilization existed but never developed fossil fuel combustion, relying instead entirely on renewable energy sources like wind, water, and muscle power, it might leave almost no detectable trace. Agriculture would still alter landscapes and create nitrogen anomalies from fertilizer use if they developed intensive farming, but these signals are subtle. Without the massive carbon pulse from fossil fuels, without the metals and plastics from industrial manufacturing, and without the radioisotopes from nuclear technology, such a civilization might be nearly invisible in the geological record despite being technologically sophisticated by pre-industrial standards. This observation connects to a deeper question about what constitutes an industrial civilization and whether industrialization is inevitable for technological development. Our own path involved coal, then oil and natural gas, then eventually nuclear power and renewables. We developed plastics, electronics, and complex manufacturing. But is this path universal? Could an intelligent species develop sophisticated technology without going through a fossil fuel phase? Perhaps they discover renewable energy sources early enough to avoid heavy reliance on combustion. Perhaps their planet lacks concentrated fossil fuel deposits. Perhaps their biology or environment pushes them toward different technological solutions. If such pathways exist, then the signatures we are looking for might be incomplete markers that only apply to civilizations that follow a trajectory similar to our own. Other technological civilizations might leave entirely different signatures that we would not recognize because we have not conceived of them. The Silurian hypothesis forces us to confront these possibilities by asking what we can actually know about the past and what remains fundamentally unknowable. Even with perfect preservation and perfect analytical techniques, there are limits to what the geological record can tell us. It records chemistry and large-scale physical changes, but it does not preserve information about culture, language, social structures, or even the appearance of the organisms that might have created those chemical signatures. If we found unambiguous evidence of an ancient industrial civilization in rocks 50 million years old, we would know almost nothing about the beings who built it beyond the fact that they consumed energy, manufactured materials, and altered their environment in detectable ways. We would not know what they looked like, how they organized their societies, what they valued, or why they disappeared. The geological record is a ledger of chemical transactions, not a history book. Yet the question persists because the stakes are so high. The Great Filter hypothesis, proposed by economist Robin Hanson, suggests that there is some barrier or obstacle that prevents civilizations from reaching the point where they become detectable across interstellar distances. This filter could lie in the past, meaning that the emergence of life and intelligence is extraordinarily rare, or it could lie in the future, meaning that civilizations tend to destroy themselves or encounter insurmountable obstacles before they achieve lasting stability. The Fermi paradox amplifies this concern. If intelligent life is common and long-lived, we should see evidence of it throughout the galaxy. The absence of such evidence suggests either that intelligence is rare, that it does not last long, or that our assumptions about how civilizations develop and spread are fundamentally wrong. Discovering that a previous industrial civilization existed on Earth and subsequently vanished would be a data point of immense significance. It would suggest that the filter lies ahead of us, that something about industrial development leads to collapse or extinction with sufficient probability that we should be deeply concerned. The precise nature of such a collapse remains speculative, but the possibilities are sobering. Climate change driven by fossil fuel combustion could render a planet uninhabitable, or severely reduce its capacity to support complex civilization. Resource depletion could undermine the material basis for technological society. Nuclear war could cause immediate catastrophic damage and long-term environmental consequences. Biological weapons, artificial intelligence, or nanotechnology might pose existential risks that become more probable as technology advances. Or perhaps the problem is more subtle, involving social collapse, loss of critical knowledge, or failure to maintain complex infrastructure over long timescales. Any of these scenarios could reduce a thriving civilization to scattered remnants within centuries, and those remnants would then face the same erasure process that affects all surface features over geological time. Understanding whether civilizations tend to survive or collapse thus becomes a question of paramount importance for our own future. We have exactly one data point, ourselves, and we're still in the middle of our own experiment with industrialization. The outcome is not yet determined. If we could add more data points by discovering evidence of previous civilizations and their fates, it would inform our choices in profound ways. This is why the Silurian hypothesis matters even though it currently lacks supporting evidence. It defines what we should look for and why we should look. The search for ancient industrial signatures intersects with another field that has developed sophisticated methods for detecting subtle anomalies in the geological record, the study of mass extinctions. Earth has experienced 5 major mass extinction events over the past 500 million years, each marked by the disappearance of a significant fraction of species in a geologically brief interval. The End-Permian extinction, roughly 252 million years ago, eliminated approximately 90% of marine species and 70% of terrestrial vertebrate species. The End-Cretaceous extinction, 66 million years ago, killed the non-avian dinosaurs along with roughly 75% of all species. These events leave clear signatures in the fossil record: a sudden drop in biodiversity, disappearance of characteristic fossils, and changes in sediment composition that reflect altered environmental conditions. What makes these extinction events relevant to the search for ancient civilizations is that they often coincide with chemical anomalies that indicate environmental catastrophe. The End-Cretaceous extinction correlates with elevated levels of iridium, an element rare in Earth's crust but common in asteroids, providing evidence for the Chicxulub impact. The End-Permian extinction shows evidence of massive volcanic eruptions in Siberia that released enormous quantities of carbon dioxide and sulfur dioxide, triggering severe climate change and ocean acidification. The End-Triassic extinction, roughly 200 million years ago, also correlates with volcanic activity and carbon cycle disruption. In each case, the extinction is not just a biological event, but a planetary-scale environmental crisis recorded in rock chemistry. If an ancient industrial civilization had existed and caused environmental damage severe enough to drive its own extinction, the signature might look similar to these natural catastrophes. A rapid injection of carbon into the atmosphere, acidification of oceans, disruption of nutrient cycles, and mass die-off of species would all appear in the geological record in ways that might be difficult to distinguish from volcanic or impact-driven extinctions. This similarity creates both an opportunity and a problem. The opportunity is that we already have extensive data on these extinction events because they are scientifically important and intensively studied. If any of them were actually caused by industrial activity rather than natural processes, the evidence might already exist in the literature, waiting to be reinterpreted. The problem is that natural explanations already exist for all the major extinctions, and these explanations are well supported by multiple lines of evidence. The End-Permian volcanism is documented by extensive flood basalt deposits in Siberia covering millions of square kilometres. The Chicxulub impact left a crater, tektites scattered across the globe, and shocked quartz in the boundary layer. Attributing these events to ancient civilizations would require explaining away the physical evidence for natural causes, which is a high bar to clear. You would need not just chemical anomalies, but positive evidence for industrial activity that could not be explained by volcanism or impacts. Nevertheless, some researchers have looked more closely at the details of these extinction events to see if any features might be consistent with industrial causes. The End-Permian extinction is particularly interesting because it unfolded over a prolonged period, possibly tens of thousands of years, with multiple pulses of extinction rather than a single catastrophic event. The carbon isotope record shows repeated negative excursions, suggesting multiple injections of carbon-13 depleted carbon into the environment. While the Siberian Traps volcanism can explain this pattern, so could a civilization that went through multiple phases of industrial expansion and collapse, each burning through available fossil fuel reserves and releasing carbon pulses. The distinction would require looking at the spatial distribution of carbon sources and whether they correlate with volcanic centres or with continental regions where coal and oil deposits would have been accessible to mining. Ocean anoxia, or oxygen depletion in seawater, accompanies several mass extinctions and provides another potential signature worth examining. Industrial pollution, agricultural runoff, and sewage discharge all contribute to eutrophication in modern oceans, where excess nutrients stimulate algal blooms that consume oxygen when they decay. Ancient anoxic events show similar patterns. Organic-rich black shales deposited in oxygen-depleted waters, elevated phosphorus levels indicating nutrient loading, and disrupted marine ecosystems. These features can be explained by natural climate warming that reduces oxygen solubility and increases nutrient runoff, but they could also be consistent with pollution from an industrial civilization. The challenge is finding geochemical markers that are uniquely industrial. Trace metals associated with mining and smelting, synthetic organic compounds, or radioisotopes from nuclear activity would provide such markers, but these have not been systematically sought in extinction boundary layers because the question was never posed. Smaller extinction events and climate perturbations that do not rise to the level of mass extinctions also deserve scrutiny. The geological record contains numerous instances of abrupt environmental change that are not fully explained. The Younger Dryas cooling event roughly 12,800 years ago saw temperatures in the North Atlantic region drop precipitously, possibly triggered by freshwater flooding from melting ice sheets, disrupting ocean circulation. The 8.2 kiloyear event involved another abrupt cooling episode. The mid-Miocene climatic optimum 15 million years ago was a period of warmth and high carbon dioxide levels that then gave way to cooling and ice sheet expansion. Each of these events has proposed natural explanations, but the underlying mechanisms are often debated and incompletely understood. Could any of them reflect industrial activity? The timeframes are generally too short and too recent for industrial signatures to be completely erased, which actually makes them potentially easier to detect if evidence exists. The lack of clear industrial markers in these relatively recent and well-studied events arguably constrains when any hypothetical ancient civilization could have existed, pushing it further back in time where detection becomes progressively harder. Trace fossils and bioturbation patterns offer another avenue for investigation that has not been fully explored in this context. Trace fossils are not body fossils, but rather the preserved evidence of organism behaviour, burrows, footprints, feeding traces, and dwelling structures. An industrial civilization would modify landscapes in ways that might leave distinctive trace patterns. Open-pit mines create geometrically regular excavations. Quarries leave vertical faces and extraction patterns. Agricultural terracing creates artificial horizontal surfaces. Urban foundations and infrastructure create underground voids and fill deposits with unusual composition. Over millions of years, these features would be deformed and buried, but certain patterns might persist. For example, extensive linear features that are too regular to be natural fractures or erosion channels could indicate roads, canals, or pipelines. The difficulty is that relatively few such features would need to survive to be detectable, and the odds of any particular structure surviving intact are extremely low. Moreover, natural geological processes can create surprisingly regular patterns through crystallization, jointing, and erosion along bedding planes. The question of scale also matters. How large would an ancient civilization need to be to leave detectable traces? Modern human civilization occupies essentially the entire planetary surface, with cities, agriculture, transportation networks, and industrial facilities on every continent. We extract resources from thousands of mine sites, drill oil wells in dozens of countries, and emit pollutants that disperse globally. This planetary scale footprint creates chemical signatures that are difficult to miss if you analyse sediment cores from multiple locations. But a smaller civilization confined to a single continent or even a single region might leave signatures that are only locally detectable. If all their industrial centres happen to be located in areas that subsequently underwent subduction or severe erosion, the evidence might be completely destroyed. Conversely, if they existed on a continent that has remained stable and accumulated thick sedimentary sequences, evidence might be preserved but only in that specific geographic location. This suggests that comprehensive global surveys would be necessary to have confidence that no ancient civilizations existed, while finding evidence in even a single location would be sufficient to confirm their existence. The statistical approach to this question involves estimating how many industrial civilizations could have existed without leaving detectable traces. This depends on multiple factors: the duration of the civilization, its energy consumption, its geographic extent, the preservation probability in different environments, and our sampling coverage of the geological record. Adam Frank and Gavin Schmidt attempted a rough calculation and concluded that civilizations lasting less than a few 100,000 years and confined to modest geographic regions could easily evade detection, especially if they existed more than a few 100 million years ago. The probability of detection increases with civilization duration and decreases with age. A civilization that lasted 10 million years would almost certainly leave unambiguous evidence. A civilization that lasted only 10,000 years and existed 500 million years ago would be nearly impossible to detect with current methods. This statistical framework leads to an uncomfortable realization about the nature of evidence and absence. We often treat the lack of discovered evidence as strong support for the conclusion that something did not exist. In many contexts, this reasoning is sound. If you search thoroughly for your keys and do not find them, you can reasonably conclude they are not where you looked. But this logic breaks down when the thing you are searching for is extremely rare, easily destroyed, and located within a search space so vast that you have only examined a tiny fraction of it. The geological record spans billions of years and represents deposits from every environment on Earth, but our actual sampling of this record is sparse. Drill cores are expensive and are primarily obtained for specific purposes: oil and gas exploration, climate reconstruction, or studying particular geological events. Most of the rock record has never been sampled at all, and even in well-studied regions, coverage is incomplete. Consider the practical realities of sediment core analysis. A typical deep-sea drilling project might retrieve cores from a dozen locations across an ocean basin. Each core represents a vertical column, perhaps a few 100 meters long and 10 centimeters in diameter. The total volume of rock sampled is minuscule compared to the total volume of sediment in the basin. Analysis of these cores is further limited by time and resources. Researchers measure specific properties relevant to their questions: isotope ratios for climate studies, fossil content for biostratigraphy, magnetic properties for dating. Running additional analyses costs money and requires justification. A scientist proposing to analyze cores for synthetic organic compounds or unusual metal distributions would need to explain why this analysis is worth funding, and without prior evidence suggesting ancient civilizations might exist, such proposals would struggle to gain support. This creates a circular problem. We have not found evidence of ancient civilizations, so we do not look for such evidence systematically, which ensures that we will not find it even if it exists. Breaking this cycle requires either stumbling upon evidence accidentally, which could happen if anomalies appear in data collected for other purposes, or mounting a deliberate search based on theoretical grounds alone. The Silurian hypothesis takes the latter approach by arguing that the question is important enough to warrant investigation regardless of prior probability. Even if the chance of finding evidence is small, the implications of a positive result are so profound that the search is justified. This is similar to the logic behind SETI, the search for extraterrestrial intelligence. We have no direct evidence that alien civilizations exist and are broadcasting radio signals, but the potential significance of detecting such signals motivates ongoing searches. The same reasoning applies to looking for ancient terrestrial civilizations. The search itself advances our understanding of what signatures civilizations leave and how those signatures degrade over time, knowledge that is valuable even if the search comes up empty. The technological requirements for such a search are not prohibitive. Most of the analytical techniques already exist and are routinely used for other purposes. What is needed is a systematic program to analyze existing sediment cores and rock samples for the full suite of potential industrial signatures: carbon isotope anomalies, synthetic organic compounds, unusual metal distributions, nitrogen isotope shifts, rare earth element patterns, and radioisotope anomalies. Ideally, this analysis would cover samples from multiple time periods and geographic locations to maximize the chance of detection. Computational methods could help by scanning databases of existing geochemical data for unusual patterns that might warrant follow-up investigation. Machine learning algorithms trained to recognize anomalies in multidimensional datasets could potentially flag samples that show combinations of features inconsistent with known natural processes. None of this is beyond current capabilities. What is lacking is the funding, coordination, and scientific consensus that the question merits serious attention. Public perception plays a role in this reluctance. The idea of ancient civilizations carries significant cultural baggage. It appears frequently in pseudoscience, conspiracy theories, and fiction, often mixed with claims about aliens, lost continents, and supernatural phenomena. Atlantis, Lemuria, and ancient astronauts have been invoked to explain everything from the pyramids to crop circles, usually without any credible evidence. This association makes serious scientists wary of engaging with related questions, even when those questions are scientifically legitimate. There is a real concern about being perceived as promoting fringe ideas or lending credibility to pseudoscientific claims. Adam Frank and Gavin Schmidt were careful to frame their paper as a thought experiment and to emphasize that they were not claiming ancient civilizations actually existed. This framing was necessary to get the work published and taken seriously, but it also limits the impact. If the hypothesis is presented only as a theoretical exercise rather than a genuine research program, it is less likely to attract the resources needed for comprehensive investigation. Yet the scientific method is designed precisely to investigate questions whose answers are unknown and might challenge prevailing assumptions. The history of science is filled with examples of ideas that seemed implausible or even ridiculous when first proposed but turned out to be correct. Continental drift, the impact theory of dinosaur extinction, and the existence of black holes all face significant skepticism before evidence accumulated to the point where acceptance became unavoidable. The possibility of ancient terrestrial civilizations deserves evaluation on its merits, based on the strength of evidence and arguments, not on whether it sounds strange or conflicts with established narratives. If the evidence points towards such civilizations existing, that conclusion should be accepted. If the evidence points away from them, that conclusion is equally valid. What is not scientifically defensible is refusing to look because the question makes us uncomfortable, or because we are confident we already know the answer. The broader implications extend beyond Earth. If we develop robust methods for detecting ancient industrial civilizations in our own geological record, those same methods could potentially be applied to other planets. Mars once had liquid water on its surface and a thicker atmosphere. If life arose there and evolved to intelligence, any civilizations that developed would have left signatures in Martian geology. Mars lacks plate tectonics, so its surface is much older than Earth's, potentially preserving evidence from billions of years ago. Several missions have returned data on Martian surface composition, and future missions could be designed to look specifically for industrial signatures. The Mars rovers carry instruments capable of detecting organic compounds and measuring elemental compositions. If these instruments found synthetic organic residues, anomalous metal concentrations, or isotopic patterns consistent with industrial activity, it would be powerful evidence. The advantage of Mars is that we can directly study surface rocks without needing to drill deep cores, though the disadvantage is that we have only examined a tiny fraction of the Martian surface in detail. Venus presents a different case. Its surface temperature of 470 degrees Celsius and pressure 90 times Earth's atmosphere make in situ exploration extremely difficult. landers have survived only minutes to hours before succumbing to the harsh conditions. However, Venus's atmosphere can be studied from orbit and from high-altitude balloons, and atmospheric chemistry might preserve signatures of past industrial activity. If a Venusian civilization had existed and burned fossil fuels or released other industrial pollutants, traces might persist in the upper atmosphere even if all surface evidence has been destroyed by heat and volcanic resurfacing. This is speculative, but it illustrates how the search for ancient civilizations could extend beyond Earth once we know what to look for. The moons of the outer solar system also warrant consideration. Europa, Enceladus and Titan have subsurface oceans or surface liquids that might support life. If intelligent life evolved in these environments, their civilizations would look very different from ours, adapted to conditions of extreme cold, high pressure and limited energy. They might never develop fire or metallurgy, fundamental technologies for human civilization. But they might develop other technologies based on chemistry, biology, or principles we have not conceived. Looking for evidence of such civilizations would require entirely different methods, but the conceptual framework is the same. Identify what signatures technological activity would leave in that environment, then look for those signatures systematically. The Silurian hypothesis, by forcing us to think carefully about what makes a civilization detectable, provides a foundation for these broader searches. The energy constraints facing any civilization provide another lens through which to examine this question. Every technological civilization requires energy to function, and the amount of energy available places limits on what that civilization can achieve. Hunter-gatherer societies operated on the solar energy captured by plants and animals they consumed, perhaps supplemented by burning wood for heat and cooking. This limited their population density and technological complexity. Agricultural societies accessed more energy by cultivating crops and domesticating animals, which allowed larger populations and more complex social structures. Industrial societies tapped into fossil fuels, which represent millions of years of accumulated solar energy compressed into concentrated deposits. This energy windfall enabled exponential growth in population, technology, and environmental impact. The progression suggests that civilizations naturally seek out increasingly concentrated energy sources to fuel their expansion. This pattern has implications for detectability. A pre-industrial civilization that never discovered fossil fuels would leave minimal geological signatures. Their carbon emissions would come only from burning wood and other biomass, which is part of the active carbon cycle and does not create the same isotopic anomalies as fossil fuel combustion. Their metal use would be limited to what could be smelted with charcoal, restricting both the quantity and variety of metals available. They might have significant cultural achievements, complex social organization, and sophisticated understanding of their world, but their environmental footprint would be relatively small and localized. Such a civilization might persist for thousands of years without leaving traces detectable in the geological record millions of years later. This creates an important distinction. The Silurian hypothesis specifically addresses industrial civilizations, those that have crossed the threshold into using fossil fuels or other concentrated energy sources at scale. Non-industrial civilizations, no matter how advanced in other ways, might be effectively invisible to geological detection methods. The transition to industrial energy use appears to be a critical juncture in a civilization's trajectory. It enables rapid technological advancement and population growth, but it also creates existential risks. Climate change from greenhouse gas emissions, resource depletion, pollution, and the development of destructive technologies all accompany industrialization. Whether this transition represents an inevitable filter that most civilizations fail to navigate successfully is one of the most important questions we face. If ancient industrial civilizations existed on Earth and subsequently collapsed or went extinct, it would suggest that the filter is real and formidable. If no such civilizations existed, it might mean that Earth's biology and geology followed a unique path that happened to enable industrial development in our case. But this path is rare in the universe. Alternatively, it might mean that civilizations that successfully navigate the industrial transition do so by finding sustainable energy sources and consumption patterns, allowing them to persist indefinitely without leaving the kind of catastrophic signatures we have been discussing. Nuclear energy introduces additional complexity to this analysis. Fission reactors use uranium and thorium, elements that exist in finite quantities in the Earth's crust. A civilization that relied heavily on nuclear fission would gradually deplete these resources and the waste products would accumulate. Current human nuclear technology produces high-level radioactive waste that remains hazardous for thousands of years. Managing this waste is one of the major challenges of nuclear energy. An ancient civilization that used nuclear power extensively might have faced the same challenges. If they stored waste in geological repositories, those repositories might still exist and might contain identifiable radioactive materials with anomalous isotope ratios. Natural uranium deposits have known isotopic compositions. Spent nuclear fuel has different ratios because the fission process consumes uranium-235 preferentially and creates plutonium and other transuranics. Finding uranium deposits with depleted uranium-235 and traces of transuranic elements would be strong evidence for ancient nuclear technology, similar to the Oklo natural reactors but with signatures that could be distinguished from natural fission. Fusion energy presents a different scenario. Fusion of hydrogen isotopes produces helium and releases energy without creating long-lived radioactive waste. A civilization that achieved practical fusion power could potentially sustain itself for billions of years using the deuterium present in seawater. Such a civilization might have a much smaller environmental footprint than one dependent on fossil fuels or fission. Their energy production would not create carbon emissions or deplete finite fuel reserves. Detection would depend on other signatures: mining operations for reactor materials, waste heat released into the environment, or synthetic materials produced using abundant fusion energy. The challenge is that a successful fusion-based civilization might be deliberately careful about its environmental impact, precisely because it has the energy and technological capacity to implement clean industrial processes. This raises the possibility that some ancient civilizations might have existed and managed their environmental footprint so well that they left minimal geological signatures. They might have deliberately avoided technologies and practices that would create long-lasting pollution, either through foresight or after learning from earlier mistakes. The concept of sustainability takes on new meaning when viewed across geological timescales. A civilization is sustainable if it can persist indefinitely without depleting its resource base or degrading its environment to the point where continuation becomes impossible. Most discussions of sustainability focus on timescales of decades or centuries, but true sustainability must function across millions of years. On this timescale, even slowly renewable resources can be exhausted if consumption exceeds regeneration rates. Topsoil erodes naturally, but is replenished through weathering of bedrock, a process that takes thousands of years. Aggressive agriculture that causes soil erosion faster than natural replenishment is unsustainable, and civilizations that depend on such agriculture will eventually face collapse when soil fertility drops below the level needed to feed their population. Historical examples like the deforestation of Easter Island or the collapse of certain Mesopotamian city-states due to soil salinization illustrate this dynamic on smaller scales. Extending this analysis to industrial resources, fossil fuels are finite on any timescale relevant to civilization. They form from organic matter buried under specific conditions over millions of years, so they are effectively non-renewable. A civilization that bases its entire energy system on fossil fuels will eventually exhaust accessible deposits and must either transition to alternative energy sources or face energy scarcity and potential collapse. Earth's fossil fuel reserves have taken hundreds of millions of years to accumulate, and we are burning through them in a matter of centuries. If an ancient civilization followed a similar trajectory, they might have depleted the fossil fuel deposits that existed in their time, and those deposits would have been partially replenished by the time humans evolved. This suggests a potential constraint on how many sequential industrial civilizations could exist on a single planet. Each one would consume available fossil fuels, and tens of millions of years would need to pass before enough new deposits form to support another industrial revolution. This timeline roughly matches the gaps between major geological periods, which might not be coincidental. Metals present a different resource picture. Unlike fossil fuels, metals are not consumed when used. Iron made into a tool or structure will eventually corrode, but the iron atoms remain in the environment and can be extracted and refined again. However, this recycling requires energy. and the distribution of metal atoms becomes progressively more dispersed with each cycle. High-grade ore deposits where metals are concentrated by geological processes are finite. Once these are mined out, future civilizations must extract metals from lower-grade sources, which requires more energy per unit of metal recovered. Eventually, the energy cost of extraction exceeds the value of the metal obtained, and that metal effectively becomes unavailable unless new extraction technologies are developed. An ancient civilization that went through an industrial phase would have mined the richest ore deposits available in their time. After their collapse and the passage of millions of years, geological processes might reconcentrate some of these dispersed metals into new ore bodies, but the total inventory of accessible high-grade ores would be reduced. This could make it harder for subsequent civilizations to develop industrial technology, creating a kind of resource filter. The question of whether intelligence and technology follow convergent evolutionary paths has direct bearing on how we interpret the search for ancient civilizations. Convergent evolution describes the phenomenon where unrelated species independently evolve similar features in response to similar environmental pressures. Wings evolved separately in insects, birds, bats, and pterosaurs. Eyes evolved independently multiple times across different animal lineages. Camera-type eyes with lenses and retinas appear in both vertebrates and cephalopods despite these groups splitting apart more than 500 million years ago. The underlying principle is that certain solutions to environmental challenges are so effective that evolution discovers them repeatedly. If intelligence and tool use follow similar convergent patterns, then any planet with complex life might eventually produce technological species. But if intelligence is a unique accident dependent on extremely specific circumstances that are unlikely to repeat, then Earth might host only one technological species across its entire history. The evidence from Earth's evolutionary history is ambiguous. Intelligence, defined as problem-solving ability and behavioral flexibility, appears in many lineages. Corvids like crows and ravens manufacture tools, recognize individual humans, and solve multi-step puzzles. Octopuses manipulate objects, learn through observation, and display individual personalities. Elephants show self-awareness, use tools, and maintain complex social structures. Dolphins communicate with signature whistles that function like names and cooperate in sophisticated hunting strategies. Chimpanzees fashion spears for hunting, use stones as hammers and anvils, and pass cultural knowledge across generations. These examples demonstrate that intelligence evolves readily and provides adaptive advantages across diverse environments. However, none of these species have developed anything approaching human-level technology. They have not discovered fire, metallurgy, agriculture, writing, or any of the other foundations of civilization. This suggests that while basic intelligence is common, the specific type of intelligence that leads to cumulative technological development might be rare. Several factors seem necessary for technological civilization to emerge. Manual dexterity is essential for manufacturing tools. Humans have opposable thumbs and precise motor control that allows manipulation of small objects. Dolphins and whales are highly intelligent but lack appendages capable of fine manipulation, which limits their ability to create physical technology. Social learning and culture are required to accumulate knowledge across generations. Each generation must be able to build on the discoveries of previous generations rather than starting from scratch. Language capable of transmitting complex abstract concepts facilitates this accumulation. Extended juvenile periods where young individuals can learn from adults appear important for transmitting accumulated knowledge. All of these features exist in humans and to varying degrees in other intelligent species, but the combination seems rare. Perhaps most importantly, there must be environmental pressure or opportunity that rewards technological development. A species that can meet all its needs through existing adaptations has no evolutionary incentive to develop technology. The specific evolutionary path that led to humans involved a series of contingent events that might not easily repeat. Our ancestors descended from trees and adopted bipedal locomotion, which freed the hands for tool use. Climate changes in Africa created pressures that favoured adaptability and problem-solving. Competition with other hominid species might have driven selection for increased cognitive abilities. The control of fire provided cooked food that made more calories available to fuel larger brains. Each of these steps was not inevitable, but rather one possible outcome among many. If any had gone differently, humans might not have evolved, and Earth's dominant intelligent species might have been something entirely different, perhaps with different capabilities and limitations. The question is whether other evolutionary paths on Earth or on other planets might lead to technological civilizations with different characteristics but similar ultimate capabilities. One intriguing possibility is that technological species might have existed in Earth's oceans rather than on land. Marine environments offer advantages and disadvantages for civilization development. Water provides thermal stability, buoyancy that reduces structural engineering challenges, and abundant resources in the form of marine life. However, fire is impossible underwater, which eliminates the most obvious path to metallurgy and chemistry. Electricity might be generated through biological means, as some fish already do, but building electrical devices underwater poses challenges. Materials science would develop along different lines, focusing on shells, bones, and organic polymers rather than metals and ceramics. Whether such a civilization could develop industrial-scale energy production and manufacturing is unclear. They might reach a sophisticated pre-industrial level and remain there indefinitely, limited by the constraints of their environment. If such a civilization existed in the past, it would leave even fainter geological signatures than a land-based industrial civilization, making detection correspondingly more difficult. The possibility of non-biological intelligence adds another layer to this discussion. If a biological civilization develops artificial intelligence or creates synthetic organisms with enhanced cognitive capabilities, these artificial beings might outlast their biological creators and continue technological development. Such intelligences might have very different goals and constraints than biological organisms. They would not require food, water, or breathable atmosphere in the traditional sense, though they would need energy and materials for maintenance and reproduction. They might be more resistant to environmental catastrophes that would destroy biological civilizations. On the other hand, they might be more vulnerable to certain failure modes like cascading system failures or resource exhaustion if they lack the adaptability of biological life. An ancient civilization might have transitioned to artificial intelligence, and their machine descendants might have persisted long after the biological originators vanished. The geological signatures of such a post-biological civilization might differ from what we've been discussing, depending on their energy sources and manufacturing processes. This speculation connects to the concept of post-singularity civilizations, societies that have undergone radical technological transformation that fundamentally alters their nature. The technological singularity refers to a hypothetical point where artificial intelligence surpasses human intelligence and begins improving itself recursively, leading to rapid and unpredictable advancement. A civilization that experiences such a transition might quickly develop capabilities that seem almost magical from our current perspective: molecular nanotechnology, matter-energy conversion, or computational substrates that could support consciousness. Such a civilization might deliberately minimize its environmental impact, or might expand to utilize all available resources in its local environment. Detection of post-singularity civilizations would depend entirely on their choices and behaviors, which are difficult to predict because they would be operating with capabilities and goals we cannot easily imagine. The anthropic principle provides yet another perspective on these questions. This principle notes that our observations of the universe are necessarily biased by the fact that we exist to make those observations. We observe a universe compatible with our existence because we could not exist in a universe that was incompatible. Applied to the question of ancient civilizations, the anthropic principle suggests that we should not be surprised to find ourselves as apparently the first technological civilization on Earth, because if we were not first, we might not exist at all. If an ancient civilization had existed and survived, they might still be here, and we would never have evolved. If they existed and went extinct but somehow prevented or delayed the evolution of subsequent intelligent species, we still would not exist. We can only observe scenarios compatible with our own existence, which necessarily excludes most scenarios involving successful ancient civilizations. This does not prove that ancient civilizations did not exist, but it does explain why their existence must have been brief, and why they must have thoroughly disappeared if they did exist. The time available for previous civilizations to have existed is constrained by the history of complex life on Earth. Multicellular organisms appeared roughly 600 million years ago. Before that, life consisted only of single-celled organisms that would not have been capable of developing technology. The Cambrian explosion 540 million years ago saw the rapid diversification of animal body plans. Vertebrates appeared in the oceans and eventually colonized land roughly 370 million years ago. Dinosaurs dominated terrestrial ecosystems from roughly 230 million years ago until their extinction 66 million years ago. Mammals diversified after the dinosaur extinction and eventually gave rise to primates. This timeline provides windows where intelligent species might have evolved. The long reign of dinosaurs is particularly interesting because it represents a major alternative evolutionary experiment. Dinosaurs were successful, diverse, and some species showed evidence of relatively complex behaviour. Could they have produced an intelligent technological species? The available evidence says no, but the evidence is limited by the same preservation biases we've been discussing. The case of dinosaurs deserves closer examination because they represent the longest period of dominance by any terrestrial vertebrate group in Earth's history. For over 160 million years, dinosaurs occupied virtually every terrestrial ecological niche, from tiny insectivores to massive herbivores weighing tens of tons. Their success is beyond question, yet none of them appear to have developed human-like intelligence or technology. The question is whether this absence is real or simply reflects gaps in our knowledge. Bird-like theropod dinosaurs showed sophisticated behaviours. They built nests, cared for their young, and some species likely lived in complex social groups. Troodon and similar dinosaurs had relatively large brain-to-body mass ratios and grasping hands with opposable digits. Some paleontologists have speculated that given another few million years of evolution, these lineages might have produced species with cognitive abilities approaching those of modern primates. But speculation is not evidence, and the fossil record shows no signs of tool use, fire manipulation, or other indicators of technological development among any dinosaur species. However, the absence of such evidence must be qualified by what we know about preservation. Behavioural traces are extraordinarily rare in the fossil record. We have thousands of dinosaur species represented by bones, but only a handful of cases where we have direct evidence of behaviour beyond basic locomotion. Fossilised nests, trackways, and coprolites provide glimpses, but these represent tiny snapshots of behaviour that happen to occur in conditions favourable for preservation. If a dinosaur species had developed early tool use, perhaps employing sticks or unmodified stones, we would likely never find evidence of this. Even among early hominids, stone tools are often the only surviving evidence of technological behaviour, and these only preserve because stone is durable and because specific fracture patterns distinguish worked stone from naturally broken rock. If dinosaurs had used organic tools that decomposed, or if their tools were behaviourally sophisticated but left no diagnostic traces, the evidence would be invisible to us. The brain structure of dinosaurs presents another challenge for interpretation. Brain tissue does not fossilise, so we infer cognitive abilities from endocasts, impressions left by the brain on the inside of the skull. These endocasts show that many theropod dinosaurs had relatively enlarged forebrains and well-developed optic lobes, suggesting complex visual processing and possibly higher cognitive functions. But translating brain structure to actual intelligence is difficult even in modern animals. Brain size relative to body size, degree of folding in the cerebral cortex, and the ratio of different brain regions all provide clues, but the relationship between these physical features and cognitive abilities is not straightforward. Crows have small brains in absolute terms, but show problem-solving abilities that rival those of great apes, demonstrating that intelligence does not scale simply with brain size. It is conceivable that some dinosaur species possessed cognitive capabilities that would surprise us if we could test them directly, but remained non-technological for other reasons related to their environment, physiology, or evolutionary pressures. One hypothesis for why dinosaurs never developed technology despite their long evolutionary tenure is that they were too successful in their ecological niches. Evolution does not produce intelligence for its own sake, but only when intelligence provides adaptive advantages that outweigh its costs. Large brains are metabolically expensive, requiring substantial energy to develop and maintain. In species where physical adaptations like size, speed, armour, or specialised feeding structures provide adequate fitness, there is no selection pressure for increased intelligence. Dinosaurs may have reached optimal adaptations for their environments through physical rather than cognitive evolution. A similar argument might apply to sharks. which have existed for over 400 million years in relatively unchanged form because their body plan is highly effective for their predatory niche. Success can paradoxically prevent the evolution of intelligence by removing the pressure that would drive cognitive advancement. The mass extinction that ended the Cretaceous period and eliminated non-avian dinosaurs reset Earth's evolutionary trajectory. In the aftermath, mammals, which had existed alongside dinosaurs for over 160 million years, but remained small and relatively unspecialized, rapidly diversified to fill vacant ecological niches. This diversification eventually led to primates and ultimately to humans. If the extinction had not occurred, mammals might have remained marginalized, and the dominant vertebrates today might still be dinosaur descendants. Whether those descendants would have eventually produced technological intelligence is unknowable, but the extinction demonstrates how contingent evolutionary outcomes are on unpredictable events. A different impact location, a slightly smaller asteroid, or different atmospheric conditions might have produced a different extinction pattern, potentially allowing some dinosaur lineages to survive and continue evolving. In such a scenario, Earth today might host an entirely different type of technological civilization, or might still be dominated by non-technological species. This contingency extends to all the potential windows in Earth's history where technological civilizations might have arisen. Each extinction event reset the evolutionary playing field and created opportunities for new lineages to radiate and explore different adaptive strategies. The end Permian extinction eliminated the dominant synapsids and allowed dinosaurs to rise. The end Cretaceous extinction eliminated dinosaurs and allowed mammals to radiate. The end Triassic, end Devonian, and Ordovician-Silurian extinctions each restructured ecosystems in fundamental ways. Between these major events, countless smaller extinction pulses and environmental shifts shaped the trajectory of evolution. Any of these transitions might have produced conditions favourable for the evolution of intelligence, or might have eliminated lineages that were trending toward greater cognitive complexity. The randomness inherent in these events means that replaying Earth's evolutionary history would almost certainly produce different outcomes, perhaps with technological species arising earlier, later, or not at all. The molecular clock, a technique that uses the rate of genetic mutations to estimate when species diverged, provides constraints on when various lineages emerged. Modern humans split from chimpanzees roughly 6 to 7 million years ago. Primates as a group emerged around 60 million years ago, shortly after the dinosaur extinction. Mammals originated over 200 million years ago but remained small and nocturnal during the age of dinosaurs. These timings are well established through both fossil evidence and genetic analysis. For an ancient non-human civilization to have existed, it would need to come from a lineage we have not identified, or one whose cognitive evolution we have not recognized. The fossil record of mammals is reasonably complete for the past 60 million years, making it unlikely that a highly intelligent mammalian lineage existed and left no trace. Going back further, the candidates become more speculative and the evidence more fragmentary. Could intelligent reptiles have existed in the Triassic period? Could amphibians have developed technology in the Carboniferous? The further back we look, the less constrained our speculation becomes, but also the less likely it seems that creatures with the necessary anatomy and physiology for technology existed. Marine reptiles like ichthyosaurs, plesiosaurs and mosasaurs dominated ocean ecosystems for millions of years, but show no evidence of unusual intelligence. They were successful predators with adaptations for swimming and hunting, but their brain structure suggests cognitive abilities similar to modern marine predators like sharks and dolphins, rather than anything approaching human intelligence. The same pattern holds for most extinct lineages. When we examine the fossil evidence, we see animals well adapted to their environments, but not trending toward the kind of generalized intelligence and manipulative ability needed for technology. This pattern is consistent with technology being a rare evolutionary outcome rather than an inevitable one, supporting the idea that humans might indeed be the first and only technological species Earth has produced. But it is also consistent with technological species being rare enough and short-lived enough that the probability of finding fossil evidence is very low, which returns us to the central problem of the Silurian hypothesis. The preservation biases that limit what we can learn from the fossil record operate with particular severity on rare species and unusual behaviours. Common organisms that lived in environments conducive to fossilization, such as shallow marine settings, are well represented in the fossil record. Rare organisms, those living in upland or forested environments, or those with unusual behaviours that occurred infrequently, are vastly underrepresented or completely absent. If an intelligent species existed but maintained a relatively small population, lived in environments where fossilization was unlikely, and practiced behaviours that left no durable traces, we would have little chance of detecting them in the fossil record, even if they persisted for hundreds of thousands of years. This is not a failure of paleontology, but rather a fundamental limitation imposed by the nature of fossilization itself. Only certain materials preserve well, only certain environments promote preservation, and only a tiny fraction of organisms that die end up fossilized. The fossil record is a biased sample that tells us much about marine invertebrates with hard shells and relatively little about terrestrial vertebrates with complex behaviours. Consider what the fossil record of modern humans will look like millions of years in the future. Human bones will occasionally fossilize, particularly those buried in caves, sedimentary deposits, or peat bogs. These fossils will allow future paleontologists to reconstruct human anatomy in considerable detail. But what about our technology and civilization? Most of our artifacts will have decomposed or corroded away completely. Cities built on coastlines will be eroded or submerged by sea level changes. Infrastructure made of steel, concrete, and glass will crumble and scatter. The plastics that seem so permanent to us will fragment and degrade over thousands to tens of thousands of years. After 1 million years, very little recognizable human technology will remain on the surface. After 10 million years, essentially nothing will be left except chemical signatures in sediments, and perhaps some objects that happen to be buried in extraordinarily favourable conditions. A paleontologist in that distant future, examining fossils of Homo sapiens, might recognise that we had relatively large brains and opposable thumbs, but they would have no way to know from bones alone that we had built cities, split atoms, or sent spacecraft to other planets. They would need to look at the geochemical record to find the carbon isotope anomaly from fossil fuel burning, the plutonium signature from nuclear testing, and the synthetic organic compounds from plastic production. Without these chemical clues, our civilization would be invisible. This thought experiment clarifies what we should expect if ancient civilizations existed. We should not expect to find their buildings or tools or vehicles. These will be gone. We should not necessarily expect to find anomalous fossils or evidence of genetic engineering. Bones are bones, and unless the engineering produced radical anatomical changes that happen to preserve, we would not detect it. What we should look for are the chemical and isotopic signatures that reflect large-scale energy use and materials production. These signatures are what the Silurian hypothesis tells us to seek, and they are signatures that could plausibly persist for tens of millions of years in the right geological settings. The question is whether anyone is looking systematically, and whether the coverage of our geological sampling is sufficient to detect such signatures if they exist. One promising avenue that has received limited attention is the analysis of amber deposits. Amber is fossilized tree resin that forms in forested environments and can preserve organisms and objects with extraordinary fidelity. Insects, spiders, small vertebrates, and even fragments of feathers and fur have been found perfectly preserved in amber, dating back over 100 million years. The resin acts as a sealant, protecting enclosed materials from decay and maintaining microscopic details that would otherwise be lost. If an ancient civilization had existed in or near forested regions, there is a small but non-zero chance that artifacts or synthetic materials might have been trapped in tree resin and preserved in amber. Modern plastics, metal fragments, processed fibres, or other artificial materials would be immediately recognisable if found in amber dated to millions of years before humans. No one is specifically looking for such anomalies because the expectation is that nothing of the sort should exist, but amber collections around the world contain millions of specimens, most of which have received only cursory examination. A systematic review of amber deposits for anomalous materials would be technically feasible and might yield surprising results. Ice cores provide another archive that has been extensively studied for climate purposes but not systematically analysed for technosignatures. The ice sheets of Antarctica and Greenland contain trapped air bubbles and chemical deposits that record atmospheric composition going back hundreds of thousands of years. Beyond this time frame, ice becomes too compressed or has been lost to flow and melting. But older ice deposits have existed at various times in Earth's history during glacial periods. Some of these ancient ice deposits have been preserved as buried glacial deposits, or have left chemical signatures in sediments that formed from glacial meltwater. These deposits might contain elevated concentrations of industrial pollutants if a civilization existed during or shortly before a glacial period. Lead, mercury, sulfur dioxide, and other pollutants released by industrial processes would have been deposited in ice and snow, creating layers enriched in these elements. Distinguishing industrial pollution from volcanic or other natural sources requires careful analysis of isotope ratios and spatial patterns. But the techniques exist and have been refined through studies of more recent pollution history. Caves and karst systems offer yet another preservation environment worth investigating more thoroughly. Limestone caves form through dissolution of carbonate rock by slightly acidic groundwater. Once formed, these caves can remain stable for millions of years if they stay below the water table or in zones protected from erosion. Cave sediments often contain fine-grained deposits that accumulate slowly and preserve delicate materials. Paleontological sites like the Cradle of Humankind in South Africa have yielded exceptionally preserved hominin fossils from cave deposits dating back several million years. Similar preservation could theoretically apply to artifacts if any ancient civilization had used caves for habitation, storage, or disposal of materials. Cave exploration and mapping efforts are ongoing in many parts of the world, but the focus is generally on accessible caves rather than systematic surveys designed to find anomalous deposits. Many cave systems remain unexplored or only partially mapped, representing potential reservoirs of undiscovered evidence. The deep subsurface represents perhaps the most challenging but potentially rewarding environment to investigate. Drill cores from deep boreholes penetrate kilometers into the Earth's crust, accessing rocks that have been protected from surface weathering and erosion for hundreds of millions of years. These cores are expensive to obtain and are primarily drilled for oil and gas exploration or geothermal energy assessment. The cores are analysed for properties relevant to these commercial purposes, such as porosity, permeability, hydrocarbon content, and temperature gradient. Additional analyses for technosignatures would require re-examining existing core collections with new questions in mind. Many research institutions and petroleum companies maintain core libraries where samples are stored for future study. A coordinated effort to analyse selected cores for unusual chemical or isotopic signatures could be undertaken without the enormous cost of drilling new holes. The challenge is selecting which cores to analyse from the vast inventory available and defining specifically what anomalies to look for. Remote sensing technologies offer capabilities that were not available until recently, and could potentially identify surface features consistent with ancient artificial structures. Satellites equipped with multispectral and hyperspectral imaging can detect subtle variations in surface composition that are invisible to the naked eye. These variations might indicate concentrations of particular minerals or chemical compounds that do not occur naturally in that context. Ground-penetrating radar and other geophysical techniques can reveal buried structures and density anomalies beneath the surface without excavation. These technologies are routinely used in archaeological surveys to locate buried ruins and artifacts from historical civilizations. Extending their application to much older time periods would require adapting search parameters and expectations, but the fundamental physics remains the same. A buried structure with different density, magnetic properties, or chemical composition than surrounding material will create a detectable anomaly, regardless of its age. The difficulty lies in distinguishing ancient artificial features from natural geological formations. Nature creates remarkably regular patterns through processes like crystallization, columnar jointing in volcanic rocks, and sedimentary bedding. The Giant's Causeway in Northern Ireland consists of hexagonal basalt columns that look almost deliberately carved but are entirely natural, formed by contraction as lava cooled. The Meraki boulders in New Zealand are nearly spherical concretions that form through precipitation of minerals around a nucleus in sedimentary rock. Without understanding the geological processes that created these features, they might be mistaken for artificial objects. Conversely, truly artificial structures that have been heavily weathered, deformed by tectonic activity, or partially destroyed by erosion might appear natural unless examined carefully. Establishing criteria that reliably distinguish ancient artifacts from natural formations is not trivial and would require extensive testing and refinement. The criteria used for recent archaeological sites, such as right angles, uniform dimensions, and tool marks, may not apply to structures that have been subjected to millions of years of geological alteration. Statistical analysis of landscape features might provide a way forward. Artificial structures, even when degraded, often exhibit regularities that are statistically unlikely to occur naturally. Parallel linear features with consistent spacing might indicate roads, walls, or agricultural terracing. Circular or rectangular depressions might indicate building foundations or excavations. Anomalous concentrations of particular materials in geometric patterns might indicate industrial sites or waste disposal areas. By analysing the statistical properties of features across large areas and comparing them to the expected distributions from natural processes, it might be possible to identify candidates that warrant closer investigation. This approach would generate many false positives because natural processes occasionally produce patterns that appear non-random by chance, but systematic follow-up could eliminate these false positives and potentially reveal genuine anomalies. Machine learning algorithms trained on both natural and artificial features could assist in this screening process, though the lack of training examples for ancient artificial features presents a challenge. The search for ancient civilizations intersects with the broader question of how common intelligence and technology are in the universe. The Fermi paradox asks why, if intelligent civilizations are common, we have not detected any evidence of them in our galaxy. The galaxy is roughly 13 billion years old, and even with slow interstellar travel, a single expanding civilization could colonize the entire galaxy within a few million years. The fact that Earth appears uncolonized and we detect no artificial signals from space suggests either that technological civilizations are extremely rare, that they do not expand beyond their home systems, that they destroy themselves quickly, or that we are not looking in the right way. The Great Filter hypothesis proposes that there is some step in the progression from non-life to spacefaring civilization that is extremely improbable. This filter might lie behind us, perhaps in the origin of life itself or the emergence of complex cells, or it might lie ahead of us, perhaps in the transition through industrial technology without self-destruction. If the filter lies behind us, then we are unusually lucky to have reached this stage, but our future prospects might be good because we have already passed the difficult hurdle. If the filter lies ahead, then many civilizations reach our current stage, but few survive the next few centuries or millennia. Discovering that an ancient civilization existed on Earth and subsequently went extinct would strongly suggest the filter lies ahead, which has sobering implications for humanity's future. It would mean that something about the development path of technological civilizations makes long-term survival unlikely. This does not predetermine our fate. Knowing that a hazard exists allows us to take precautions and potentially avoid it, but it would transform the existential risks we face from abstract possibilities into documented historical precedents. The question would shift from whether collapse is possible to what specifically caused previous collapses and how we might avoid the same outcome. Different types of collapse scenarios leave different signatures in the geological record. A rapid collapse caused by nuclear war would potentially leave radioisotope signatures concentrated in a thin layer, along with carbon isotope anomalies from the fires that would follow nuclear detonations. A slower collapse caused by climate change and resource depletion might show a more gradual decline in industrial signatures over thousands of years as the civilization consumed remaining resources and contracted. A biological catastrophe like an engineered pandemic might leave little trace beyond an extinction marker in the fossil record, showing a sudden drop in population of a particular species. The nature of the collapse matters because it determines what evidence we should look for and how we might recognize it. A civilization that gradually transitioned to sustainability and persisted for millions of years would leave a very different signature than one that burned brightly and died quickly, and both would differ from one that transitioned away from industrialization entirely. The possibility that civilizations might deliberately limit their detectability introduces another complication. A civilization that recognizes the dangers of resource depletion and environmental damage might consciously reduce its footprint, developing technologies that work with natural cycles rather than against them. Such a civilization might use renewable energy exclusively, practice closed-loop recycling, and maintain stable population levels in equilibrium with their environment. Over millions of years, they might leave minimal geological signatures because their activities would not create the kinds of massive chemical perturbations that industrial fossil fuel combustion produces. This would make them effectively invisible using the detection methods we have been discussing. We would be looking for catastrophic signals when what we should be looking for are signs of careful stewardship. Distinguishing deliberate sustainability from simple absence is nearly impossible without additional context. This raises philosophical questions about what we hope to learn from discovering ancient civilizations. If we find evidence of collapse, we gain a warning but little guidance on how to avoid the same fate without understanding the specific mechanisms that led to failure. If we find no evidence at all, we remain uncertain whether that indicates absence of previous civilizations or merely the inadequacy of our detection methods. If we find evidence of long-term sustainability, we would want to understand how they achieved it, but the geological record preserves chemistry and isotopes, not social structures or decision-making processes. The knowledge that sustainability is possible across deep time would be valuable, but extracting the lessons that would allow us to replicate that achievement might prove impossible. Nevertheless, the search remains worthwhile because even partial information constrains possibilities and informs our understanding of what paths are available to technological civilizations. The mathematical framework for estimating the probability of ancient civilizations draws on similar logic to the Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy. The Drake equation multiplies together factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life arises, the fraction where intelligence evolves, the fraction that developed technology, and the average lifetime of technological civilizations. Each factor is uncertain, and multiplying uncertainties together produces even greater uncertainty in the final result. A similar approach can be applied to Earth's history. Start with the total time window where complex life has existed, roughly 600 million years. Divide this into intervals where conditions might have been suitable for technological species to evolve. Estimate the probability that intelligence evolves in any given interval. Estimate the probability that such intelligence develops technology. Estimate how long such a civilization might persist. Multiply these factors together to estimate the expected number of technological civilizations that have existed on Earth. The problem is that most of these factors are deeply uncertain because we have only one example: ourselves. We know that intelligence evolved at least once, but we do not know if the probability is 1 in 10 or 1 in a million per interval. We know that technological civilization has persisted for at least a few centuries, but we do not know if the typical duration is thousands of years or millions. Without additional data points, the calculation becomes an exercise in selecting assumptions that produce whatever answer we find philosophically satisfying. If we assume intelligence is common and civilizations are short-lived, we conclude that many ancient civilizations likely existed but all failed quickly and left minimal trace. If we assume intelligence is rare and civilizations are potentially long-lived, we conclude that we are probably the first and face an uncertain future. The data do not currently distinguish between these scenarios, though the absence of obvious industrial signatures in well-studied geological sequences provides some weak evidence against very common short-lived civilizations, since probability would suggest we should have found something by now if they were truly numerous. Bayesian reasoning offers a more sophisticated approach to updating our beliefs based on available evidence. Start with a prior probability for ancient civilizations based on theoretical considerations. Then update this probability based on the evidence we have observed. The challenge is that absence of evidence provides only weak constraint when the evidence would be difficult to detect even if present. If we have searched only a small fraction of the relevant geological record, and if the signatures we are looking for would be subtle and easy to miss, then finding nothing so far changes our probability estimates only slightly. This is mathematically encoded in Bayes' theorem through the likelihood ratio, which compares the probability of observing the evidence given that the hypothesis is true versus the probability of observing the same evidence given that the hypothesis is false. When both probabilities are similar, meaning we would expect to find roughly the same result whether or not ancient civilizations existed, the evidence provides little discriminatory power. Alternative evolutionary pathways represent another dimension of uncertainty. We tend to assume that technological civilizations will resemble humans in having bilateral symmetry, differentiated limbs, large brains concentrated in a head region, and carbon-based biochemistry using DNA. But life on Earth shows remarkable diversity in body plans and biological strategies. Octopuses have distributed nervous systems, with significant neural processing occurring in their arms rather than concentrated in a central brain. Slime molds exhibit problem-solving behaviours despite lacking neurons entirely, using chemical signalling to navigate mazes and find food efficiently. Eusocial insects like ants and bees display collective intelligence that emerges from the interactions of millions of individuals, none of which are particularly intelligent alone. Could a eusocial species develop technology? Imagine an ant colony with 10 million individuals working collectively, where specialised castes develop tool use, construction, and problem-solving capabilities. The colony as a whole might qualify as intelligent even though individual ants remain simple. Such a species might build structures and manipulate their environment in sophisticated ways, but those structures would be organic and would decay rapidly after the colony's demise, leaving little trace. Plant intelligence represents an even more alien possibility. Plants respond to their environment, communicate through chemical signals, and some species like the Venus flytrap show rapid responses to stimuli. While plants lack the centralized nervous systems and rapid information processing that characterize animal intelligence, they process information and make decisions over longer timescales. Could a plant species or plant-based ecosystem develop something analogous to technology? It is difficult to imagine given their sessile nature and slow response times, but truly alien intelligence might operate on principles we have not conceived. If such intelligence existed in Earth's past, we would not recognize it, because our definition of intelligence and technology is shaped by our own mammalian, bilateral, fast-moving experience. This is the challenge of searching for the truly unknown. We risk finding only what we already expect to exist. The subsurface biosphere adds yet another layer of complexity. Microorganisms exist kilometers deep in the Earth's crust, living in rock pores and fractures, metabolizing minerals and existing in near isolation from the surface world. These organisms process information at the molecular level and respond to their environment, but calling them intelligent stretches the definition past usefulness. However, the fact that life exists in these extreme environments, often at very low densities and energy levels, suggests that biological activity is more pervasive and persistent than surface observations might indicate. If an ancient surface civilization existed and collapsed, microbial communities might have adapted to utilize their industrial waste products, creating ecological niches that persisted long after the civilization vanished. These microbial communities might show unusual metabolic capabilities or genetic sequences that reflect adaptation to artificial compounds. Searching for such signatures would require surveying subsurface microbial diversity, specifically looking for adaptations to synthetic materials, a project that has not been undertaken because the question has not been posed. The concept of archaeological horizons provides a useful framework for thinking about detectability across different timescales. In conventional archaeology, a horizon refers to a layer containing artifacts from a particular period, and these horizons can be dated and correlated across sites. For civilizations millions of years old, we would be looking for chemical or isotopic horizons rather than artifact horizons. A thin layer in sedimentary rock showing simultaneous carbon isotope anomalies, elevated metal concentrations, and synthetic organic residues would constitute such a horizon if it could be demonstrated to represent a synchronous global event rather than localized conditions. The challenge is establishing both the synchronicity and the global extent. Sediment layers from different locations can be difficult to correlate precisely when dealing with timescales of millions of years. Dating techniques have uncertainties that expand with age, so a layer dated to 50 million years ago might actually represent any time within a window of several 100,000 years. This temporal smearing makes it difficult to prove that anomalies detected in different locations represent the same event. Volcanic ash layers provide one of the best tools for correlation because they deposit rapidly across large areas and contain minerals that can be chemically fingerprinted to identify the specific eruption that produced them. If an industrial civilization's chemical signature appeared in sediments immediately above or below a distinctive ash layer, that would provide a temporal anchor point. Multiple cores from different locations showing the same association would strengthen the case for a real global signal rather than localized anomalies. No such associations have been reported, but again, no one has been systematically looking for them. The existing literature on volcanic ash layers focuses on their use for dating and correlating other geological events, not on examining adjacent sediments for technosignatures. Reanalyzing existing datasets with this specific question in mind could potentially reveal patterns that were previously overlooked because they were not expected. Oxygen isotope ratios in the shells of foraminifera and other marine organisms reflect both the temperature of the water where they lived and the total amount of water locked up in ice sheets. By measuring oxygen isotopes in cores from different ocean basins, researchers have constructed a detailed history of global temperature and ice volume going back millions of years. This isotope stratigraphy allows correlation of sediment layers across vast distances with reasonable precision. If industrial carbon emissions caused rapid warming and ice sheet collapse, the oxygen isotope record should show a distinctive signal. The problem is that natural climate variations also produce warming and cooling cycles, so distinguishing an industrial signal from a natural one requires additional evidence. The combination of oxygen isotope changes indicating warming, together with carbon isotope anomalies indicating fossil fuel combustion, would be more diagnostic than either signal alone. The ratio of strontium-87 to strontium-86 in the ocean changes slowly over millions of years, due to weathering of continental rocks and hydrothermal alteration of oceanic crust. This ratio is globally uniform at any given time because ocean mixing is relatively rapid, compared to the processes that alter strontium isotopes. Marine organisms incorporate strontium into their shells with the same isotope ratio as seawater, so measuring strontium isotopes in fossils allows dating and correlation. If strontium isotope ratios showed sudden anomalous shifts that could not be explained by changes in weathering rates or volcanism, it might indicate artificial alteration of ocean chemistry through industrial processes. Certain mining and manufacturing operations release strontium with different isotopic compositions than natural sources, so large-scale industrial activity could potentially perturb the ocean's strontium isotope ratio, creating a detectable anomaly. The principle emerging from all these examples is that multiple independent lines of evidence are necessary to make a convincing case. Any single anomaly can be explained away as a measurement error, contamination, or unusual but natural process. But when multiple different isotope systems, chemical markers, and geological observations all point to the same conclusion and all appear in the same narrow time interval, the probability of coincidence becomes vanishingly small. This is how scientific consensus is built around major findings. The meteorite impact theory for dinosaur extinction became widely accepted only after multiple lines of evidence accumulated. The iridium anomaly, shocked quartz, tektites, the Chicxulub crater, and correlation of these features with the extinction horizon. Any one of these could have been explained alternatively, but together they form a coherent picture that is difficult to dispute. A similar standard of evidence would be required to establish the existence of an ancient civilization. The political and social dimensions of this search cannot be ignored. Research funding is limited, and proposals must compete for resources based on their perceived merit and likelihood of producing significant results. A proposal to search for evidence of ancient civilizations faces skepticism because the prior probability is considered low, and because the topic carries associations with pseudoscience. Reviewers might question whether the resources would be better spent on questions where the probability of meaningful results is higher. This creates a catch-22 situation. We cannot know the true probability without searching systematically, but we cannot get funding to search systematically without demonstrating high probability. Breaking this deadlock requires either serendipitous discoveries that force the question onto the agenda, or champions within the scientific community who are willing to advocate for the work despite the skepticism. Adam Frank and Gavin Schmidt's paper helped by lending credibility to the question and showing that it could be addressed scientifically. But translating that theoretical framework into actual funded research programs remains a challenge. Public interest could potentially drive research in this area even without traditional funding sources. Crowdfunding has supported various scientific projects in recent years, and the question of ancient civilizations has inherent appeal to many people. However, public interest can be a double-edged sword. It attracts attention and resources, but also invites sensationalism and misinterpretation. Popular media often presents scientific speculation as established fact or exaggerates findings to create dramatic narratives. Researchers working on these questions must navigate the tension between engaging public interest and maintaining scientific rigor. Clear communication about what is known versus what is speculated, about the limitations of evidence, and about the difference between plausible hypotheses and demonstrated facts becomes especially important when dealing with topics that capture popular imagination. The ethical dimensions deserve consideration as well. If we discovered conclusive evidence that an ancient industrial civilization existed and collapsed, how should that information be communicated? The knowledge that previous civilizations failed to survive their industrial phase could trigger despair and fatalism, or it could motivate urgent action to avoid the same fate. The framing matters enormously. Emphasizing that we have the capacity to learn from past failures and choose different paths provides a constructive message. But ensuring that message is received rather than being overwhelmed by apocalyptic narratives would require careful thought. Scientists have a responsibility to present findings accurately, while also considering how those findings will be interpreted and applied. This is not an argument for suppressing information, but rather for being thoughtful about context and communication when dealing with questions that have profound implications for how humanity views its place in history and its prospects for the future. The search for ancient technosignatures also connects to the emerging field of astrobiology and the search for biosignatures on exoplanets. As telescopes become powerful enough to analyze the atmospheric composition of planets orbiting other stars, astronomers are developing techniques to identify chemical signatures that might indicate biological activity. Oxygen in an atmosphere can be produced by photosynthesis. Methane combined with oxygen creates a disequilibrium that suggests biological sources because these gases react together unless continuously replenished. Phosphine in the atmosphere of Venus was recently proposed as a possible biosignature, though this interpretation remains controversial. The same logic applies to technosignatures. Certain atmospheric compositions might indicate industrial activity rather than purely biological or geological processes. Chlorofluorocarbons, for instance, are entirely synthetic and would be unambiguous markers of industrial chemistry if detected in an exoplanet atmosphere. Extending this framework back to Earth's history, we can ask what our own atmosphere looked like during different geological periods and whether any anomalies might indicate ancient industrial activity. Ice core records extend back only hundreds of thousands of years, but atmospheric composition can be inferred from proxy measurements in older rocks. For example, the ratio of different ion oxidation states in ancient soils reflects atmospheric oxygen levels. Carbon dioxide levels can be estimated from the isotopic composition of carbonates and from stomatal density in fossilized leaves, since plants adjust their stomata based on atmospheric carbon dioxide. Methane concentrations affect the hydrogen isotope ratio in organic matter through complex photochemical reactions. By combining multiple proxies, researchers have reconstructed atmospheric history going back hundreds of millions of years. These reconstructions show natural variations driven by volcanism, weathering, evolution of photosynthetic organisms, and other processes. But could they also contain signals of industrial activity that have been attributed to natural causes because no one suspected an alternative explanation? The most promising candidates would be periods of rapid atmospheric change that are difficult to explain through known natural mechanisms. The late Paleocene thermal maximum mentioned earlier represents one such event. Another is the End-Permian crisis, which involved extreme warming, ocean acidification, and massive carbon release. The Cretaceous ocean anoxic event saw widespread oxygen depletion in marine environments, accompanied by carbon burial and climate warming. Each of these events has proposed natural explanations involving volcanism, methane hydrate release, or ecosystem collapse cascades. But the details remain debated, and in some cases the proposed mechanisms seem insufficient to explain the observed magnitude and rapidity of change. This does not mean these events were caused by industrial civilizations. It means our understanding of natural Earth system dynamics is incomplete. The possibility of industrial causes should be included in the hypothesis space to be tested against evidence, rather than excluded by assumption. Testing these hypotheses requires specific predictions about what would be different if an event were industrial, rather than natural. Industrial fossil fuel combustion would preferentially release carbon from coal, oil, and gas deposits that have distinctive isotopic signatures and often contain trace elements or organic biomarkers characteristic of the geological formation they came from. Natural carbon release from volcanism involves carbon that has been deeply recycled through the mantle and has a different isotopic composition. Methane hydrate release involves carbon from recent organic matter buried in seafloor sediments. By analysing not just the quantity of carbon released, but its detailed isotopic and chemical composition, it should be possible to distinguish between these sources. Similarly, industrial processes release specific combinations of metals and other elements in ratios that differ from volcanic emissions. Smelting copper ore releases different trace elements than volcanic copper deposits. Manufacturing cement releases carbon dioxide with distinctive oxygen isotopes due to the chemical reactions involved. Each industrial process has a geochemical fingerprint that could in principle be detected if preserved in the geological record. The key is developing sufficiently detailed geochemical models that predict exactly what signatures to look for. This requires understanding industrial processes at a fundamental level and then projecting how those chemical signatures would evolve over millions of years as they are diluted, dispersed, transformed by diagenesis, and potentially concentrated by secondary geological processes. Some signatures will fade rapidly while others might persist or even become enhanced. For instance, synthetic organic compounds might be broken down into simpler molecules, but if those breakdown products are unusual and stable, they could accumulate to detectable levels even as the original compounds vanish. Heavy metals released by smelting might be dispersed by erosion, but then reconcentrated in sediments where they precipitate as sulfides or carbonates, creating anomalous ore bodies that would be recognizable if their distribution and composition differ from typical ore deposits formed by hydrothermal or sedimentary processes. This brings us to an intriguing possibility. What if some ore deposits that geologists have attributed to natural processes were actually created by ancient industrial activity? Certain types of ore deposits show features that are difficult to explain through conventional models. Mississippi Valley-type lead-zinc deposits consist of sulfide minerals that precipitated from low-temperature fluids in limestone formations, but the source of the metals and the mechanism that concentrated them remain subjects of debate. Could some of these deposits represent industrial waste or tailings from ancient mining and smelting that have been geologically processed and reconcentrated? The chemistry would need to be examined carefully to test this hypothesis, looking for isotopic ratios or trace element patterns inconsistent with natural ore formation. Similarly, some phosphate deposits that are mined for fertilizer show unusual concentrations and distributions. While most are clearly marine in origin, formed from the accumulation of bone and organic matter in oxygen-poor environments, could some represent artificial phosphate concentration from ancient agriculture? These speculations venture into territory where mainstream geology would rightly demand extraordinary evidence before accepting extraordinary claims. The burden of proof lies with anyone proposing that conventional geological interpretations are incorrect, but the exercise of asking these questions serves a purpose even if the answers turn out to be conventional. It forces more rigorous examination of the evidence and the assumptions underlying our interpretations. Geology, like all sciences, advances by questioning established models and seeking evidence that might refute them. The expectation that all deposits are natural should not prevent testing whether any might have artificial origins. The expectation that atmospheric changes are driven by natural processes should not prevent looking for industrial signatures. Science progresses through skepticism, applied equally to conventional wisdom and to new hypotheses, letting evidence rather than expectation determine conclusions. The long-term fate of industrial materials provides another angle for investigation. Where does everything go after a civilization collapses? Steel corrodes to iron oxide, which is chemically indistinguishable from natural rust and disperses into soil and sediment. But the distribution might be anomalous, showing elevated iron concentrations in unexpected locations or geological contexts. Aluminum, which is one of the most abundant elements in Earth's crust but does not occur naturally in metallic form, corrodes to aluminum oxide, which is chemically identical to the mineral corundum. Large quantities of corroded aluminum might create corundum concentrations in unusual settings. Copper corrodes to various copper minerals including malachite, azurite, and chalcocite, which are also found naturally but might show distinctive distributions or associations if they originated from artifacts rather than ore deposits. Glass is chemically similar to many natural silicate minerals and volcanic glass, but manufactured glass has a different structure at the molecular level and often contains additives like lead or sodium that create distinctive compositions. The question of statistical significance becomes central when evaluating potential evidence. Natural processes create enormous variability in the geological record. Metal concentrations, isotope ratios, and organic compound distributions all vary naturally across space and time due to local conditions, biological activity, and geological processes. Detecting an artificial signal against this background requires demonstrating that an observed anomaly is statistically unlikely to occur by chance. This is straightforward when the anomaly is large and unambiguous, like the iridium spike at the Cretaceous-Paleogene boundary that is 2 orders of magnitude above background levels. It becomes much more difficult when the anomaly is subtle, perhaps only 2 or 3 times background, because natural variability can occasionally produce such excursions. Distinguishing signal from noise requires either very large data sets that allow statistical analysis of many samples, or multiple independent anomalies that correlate with each other in ways that are improbable if each occurred independently. The spatial distribution of anomalies provides additional discriminatory power. Industrial activity concentrates in specific locations: cities, manufacturing centres, mining districts, transportation corridors. Even after millions of years of erosion and geological reworking, some spatial structure might persist in the distribution of chemical signatures. If elevated metal concentrations appear in patterns that are inconsistent with natural ore-forming processes but consistent with industrial sources, this would be suggestive. Natural ore deposits form through hydrothermal circulation, magmatic differentiation, or sedimentary concentration, each of which creates characteristic spatial patterns. Hydrothermal deposits cluster around volcanic centres or along fault zones. Sedimentary deposits follow ancient coastlines or river systems. Industrial deposits would show different patterns reflecting human geography rather than geological constraints. The difficulty is that after tens of millions of years, tectonic deformation, erosion, and sediment transport scramble spatial patterns, making it progressively harder to recognise artificial distributions. Temporal clustering provides another diagnostic. If multiple independent chemical anomalies all appear in the same narrow time interval, this suggests a common cause rather than independent natural events that happen to coincide. The probability of coincidence can be calculated from the frequency and duration of individual events. If carbon isotope excursions occur randomly, once every 10 million years and last 10,000 years on average, the probability of one occurring in any given century is roughly 1 in 100,000. If synthetic organic compounds appear with similar frequency and duration, the probability of both occurring in the same century is roughly 1 in 10 billion. As you add more independent markers, the probability of natural coincidence drops exponentially. This is the power of convergent evidence. Individually plausible events become collectively implausible, forcing consideration of alternative explanations. However, this reasoning only works if the markers are truly independent. If industrial activity causes carbon isotope anomalies and synthetic compound production simultaneously, these are not independent events but rather different consequences of the same cause. The statistical argument requires markers that are independent under the null hypothesis of natural causation, but correlated under the alternative hypothesis of industrial activity. For example, carbon isotope anomalies from volcanic degassing would not correlate with synthetic organic compounds because volcanoes do not produce polymers. But industrial civilization would produce both. Finding them together supports the industrial hypothesis over the volcanic hypothesis. This is why it is essential to consider multiple types of evidence rather than relying on any single marker, and why the absence of systematic searching is so frustrating to those who take the question seriously. The role of peer review and scientific conservatism must also be acknowledged. Science advances through a balance between openness to new ideas and skepticism of extraordinary claims. When someone proposes a radical hypothesis that contradicts established understanding, the scientific community rightfully demands strong evidence before accepting it. This conservatism serves an important function. It prevents the field from being overwhelmed by incorrect ideas and maintains the reliability of scientific knowledge. But it can also delay acceptance of correct ideas that challenge prevailing paradigms. The history of science includes many examples where initially controversial ideas later became mainstream. Plate tectonics, the bacterial origin of ulcers, the existence of exoplanets, the impact theory of dinosaur extinction. Each faced significant resistance before accumulating enough evidence to overcome skepticism. The question of ancient civilizations currently sits in this uncertain territory. The hypothesis is scientifically testable, the implications are significant, but the evidence is not yet compelling enough to overcome the prior improbability assigned by most scientists. Moving the question forward requires work on multiple fronts. Theoretical development is needed to refine predictions about what signatures to expect and how they would evolve over geological time. Analytical development is needed to improve detection limits and measurement precision for relevant markers. Observational programs are needed to systematically analyze appropriate samples rather than relying on serendipitous discoveries. And perhaps most importantly, communication is needed to explain to the broader scientific community why the question matters and deserves serious investigation. This communication must avoid the trap of overstating the current evidence while still conveying the legitimate scientific interest in the question. It is a difficult balance, but one that scientists working in other controversial areas have navigated successfully. The potential for false negatives must be considered alongside the potential for false positives. A false positive would occur if we mistakenly identified natural features as evidence of ancient civilization. This is clearly undesirable because it would lead to incorrect conclusions and waste resources chasing a phantom. But a false negative, failing to recognize evidence that actually exists, is also undesirable because it leaves us ignorant of important information about Earth's history and the fate of civilizations. Current scientific culture strongly penalizes false positives through peer review and replication requirements, which is appropriate. But this creates an asymmetry where false negatives receive less attention. If evidence of ancient civilizations exists but is not recognized because no one is looking, or because the evidence does not fit expected patterns, we suffer the consequences of ignorance without even knowing what we are missing. Balancing these risks requires calibrating skepticism to be neither too permissive nor too restrictive. The timeline for resolving this question depends on commitment of resources and attention. If the scientific community decided this was a priority and dedicated substantial funding to systematic searches, preliminary results could emerge within years. Analysing existing core collections for technosignatures would be relatively quick because the samples already exist. Developing and testing new analytical methods would take longer, but could proceed in parallel. Drilling new cores in strategically selected locations would take longer still, and would depend on specific targets identified through preliminary work. Over a decade or two of focused effort, the question could be resolved with far greater confidence than we currently have. Either clear evidence would emerge, substantially raising the probability that ancient civilizations existed, or the absence of evidence after comprehensive searching would substantially lower that probability. Currently, we are in a state of maximum uncertainty, and the path forward for reducing that uncertainty is reasonably clear, even if the will to pursue it remains limited. The implications of discovering ancient civilizations extend beyond academic curiosity into practical domains that affect humanity's future trajectory. Climate science would be transformed by concrete examples of how industrial activity affects planetary systems over long timescales. Currently, climate models project future warming and ecosystem changes based on physical principles, paleoclimate analogues from periods with different carbon dioxide levels, and observations of the current warming trend, but we have no examples of what happens when an industrial civilization runs its full course through expansion, peak resource consumption, and whatever comes after. An ancient civilization that caused significant warming and then collapsed would provide a case study of the feedbacks, tipping points, and long-term consequences that current models can only approximate. The geological record of their climate impact would constrain model parameters and validate or refute particular feedback mechanisms. This knowledge would be invaluable for improving predictions of Earth's future climate trajectory under different emission scenarios. Resource management would similarly benefit from historical precedent. Modern concerns about peak oil, mineral depletion, topsoil erosion, and aquifer exhaustion are based on projecting current consumption rates forward and comparing them to estimated reserves. But these estimates are uncertain, and the consequences of actual depletion are incompletely understood because we have never experienced it on a global scale. If an ancient civilization depleted their fossil fuel reserves, mined their richest ore deposits, and exhausted their most productive agricultural lands, the geological record of this process and its consequences would inform our own resource planning. we could see which resources proved to be truly limiting, which technologies or practices allowed them to extend or substitute resources, and what ultimately constrained their civilization's scale and duration. This is information that cannot be obtained from first principles or small-scale experiments. It requires observing the full arc of industrial civilization, something we are currently experiencing in real time but would benefit from having additional data points for comparison. The search for extraterrestrial intelligence would be reframed by knowledge of ancient terrestrial civilizations. The Drake equation and Fermi paradox discussions assume certain probabilities for the emergence and longevity of technological civilizations based largely on theoretical reasoning. If Earth has produced multiple technological civilizations over its history, this would dramatically increase estimates of how common such civilizations are in the galaxy, but simultaneously provide evidence that their longevity is limited since none of Earth's previous civilizations survived to the present. This combination of high emergence probability and low survival probability would have profound implications for SETI strategy. Rather than searching for long-lived civilizations that have been broadcasting for millions of years, we should focus on detecting civilizations during their relatively brief technological phase. This changes what wavelengths to monitor, what types of signals to look for, and how to allocate observing time across different targets. It also changes the expected outcome of the search. Instead of hoping to find ancient, stable civilizations that could serve as mentors, we should expect to find civilizations in various stages of their life cycle, many of which might be facing the same existential challenges we face. Philosophical and cultural implications would be equally profound. Human exceptionalism, the idea that humanity occupies a unique position in the history of life on Earth, would be fundamentally challenged by evidence of previous civilizations. Religions and worldviews built on the premise that humans are the first or only bearers of intelligence and purpose would need to accommodate the reality of predecessors who also achieved consciousness, culture, and technology. This could be interpreted in various ways depending on religious and philosophical frameworks. Some might see it as humbling evidence that we are one instance of a recurring pattern rather than a unique creation. Others might interpret it as evidence of purpose or design operating at timescales beyond what was previously conceived. The diversity of possible interpretations means that the cultural impact would vary across different societies and traditions, but few worldviews would emerge unchanged. The concept of progress would require re-examination. Modern Western thought generally views history as directional, moving from primitive to advanced states, with temporary setbacks but overall accumulation of knowledge and capability. This narrative of progress assumes we are at or approaching the peak of human achievement, that our knowledge is greater than any previous humans possessed. Discovering that previous civilizations reached industrial levels comparable to, or exceeding our own, only to collapse and leave future generations to rebuild from scratch, would demonstrate that progress is not inevitable or permanent. Knowledge can be lost, capabilities can be gained and then forfeited. Civilizations can rise, flourish, and vanish, leaving those who come after to rediscover what was once known. This cyclical or episodic view of history has precedents in various philosophical and religious traditions, but is not the dominant narrative in contemporary industrial societies. Confronting concrete evidence of previous rises and falls would force a more nuanced understanding of what progress means and whether current trajectories are sustainable or merely temporary peaks. Risk assessment for existential threats would shift from abstract possibility to documented precedent. Currently, discussions of existential risk involve scenarios that have never occurred: global nuclear war, runaway climate change, artificial intelligence misalignment, engineered pandemics, nanotechnology accidents. These are taken seriously by some researchers and policymakers, but remain hypothetical to most people. Finding evidence that an ancient civilization actually experienced collapse due to environmental destruction, resource depletion, or technological catastrophe would transform these abstract scenarios into historical events. The psychological and political impact of this shift could be substantial. It is easier to dismiss scenarios that have never happened as unlikely or exaggerated. It is much harder to dismiss scenarios that demonstrably occurred in the past. This could catalyze more urgent action on mitigating existential risks, or conversely could induce fatalism if the collapse of previous civilizations is interpreted as inevitable rather than avoidable. The framing and communication of such findings would be critical to determining which response dominates. The educational implications would ripple through multiple disciplines. Geology curricula would need to incorporate the possibility of anthropogenic or technogenic processes operating at various points in Earth's history, not just in the Anthropocene. Students would learn to consider industrial signatures alongside volcanic, tectonic, and climatic explanations when interpreting anomalies in the geological record. Biology courses would address whether intelligence and technology represent convergent evolutionary solutions that arise repeatedly, or rare accidents dependent on highly specific circumstances. History and anthropology would expand their scope beyond the few thousand years of recorded human civilization to consider the possibility of civilizations separated by millions of years, with no cultural or genetic continuity between them. The very definition of history might expand from the study of written records to the study of all intelligent civilizations, whether or not they left linguistic artifacts. The methodological lessons would extend beyond the specific question of ancient civilizations. Science operates through a combination of induction from observations, deduction from theoretical principles, and testing of hypotheses against evidence. The search for ancient civilizations highlights the challenges that arise when observations are sparse, theory is underdeveloped, and testing is difficult. These same challenges appear in many frontier areas of science: the search for dark matter, the origin of life, the nature of consciousness, the evolution of the universe before the cosmic microwave background became transparent. In each case, scientists must work with incomplete information, develop methods for extracting signal from noise, and guard against both premature conclusions and excessive skepticism. The intellectual tools developed for one problem often prove valuable for others, so advancing methodology for detecting ancient civilizations could yield benefits for seemingly unrelated fields. The question of burden of proof deserves careful consideration. In most contexts, the burden lies with those proposing a new or extraordinary claim. If someone claims ancient civilizations existed, they must provide convincing evidence. It is not the responsibility of skeptics to prove they did not exist. This is a reasonable general principle because it prevents scientific literature from being cluttered with unsupported speculation. However, this framing can become problematic when applied to questions where absence of evidence genuinely reflects absence of searching rather than absence of phenomenon. If no one has systematically looked for technosignatures in the geological record, then failing to find them tells us little. The absence of evidence is not evidence of absence when the evidence would be difficult to detect and has not been sought. In such cases, the scientific community has a collective interest in conducting sufficient investigation to move beyond ignorance, even if no individual researcher can justify the effort based on conventional risk-reward calculations for their career. This highlights a structural problem in how scientific research is organised and funded. Individual researchers pursue questions where they can demonstrate feasibility and high probability of publishable results within grant timescales of a few years. Program officers and review panels evaluate proposals based on track records, preliminary data, and likelihood of success. This system works well for incremental advancement of established fields, but is less effective for high-risk, high-reward questions that require substantial investment before knowing whether the answer will be positive or negative. The question of ancient civilizations falls into this category. Systematic searching would require significant resources and might yield no positive results, which would be scientifically valuable in constraining possibilities, but would be difficult to publish in high-impact venues and might be perceived as a career setback for researchers involved. Overcoming this requires either institutional commitment from funding agencies and universities to support such work explicitly, or alternative funding mechanisms that are less risk-averse. Crowdfunding and private philanthropy represent possible alternatives. Several large-scale scientific projects have been funded privately in recent years. The Breakthrough Listen project searching for extraterrestrial intelligence, the Allen Telescope Array for radio astronomy, and various space exploration initiatives by private companies. Individuals and foundations with resources and interest in fundamental questions can support work that might not compete successfully for traditional government grants. The challenge is ensuring that privately funded science maintains the same standards of rigor and openness as publicly funded work. Peer review, data sharing, and publication in reputable journals are essential regardless of funding source. Private funding can enable questions to be addressed that might otherwise be neglected, but it should complement rather than replace public investment in science, and it must be structured to preserve scientific integrity and independence. The timeline of Earth's history provides specific windows where ancient civilizations are more or less plausible, based on biological and geological constraints. Before the Cambrian explosion roughly 540 million years ago, animal life consisted of simple organisms that left limited fossil evidence. The cognitive abilities and manipulative capabilities required for technology almost certainly did not exist in this period. Between the Cambrian and the Devonian period, roughly 420 million years ago, life was dominated by invertebrates and early fish. Again, the anatomical requirements for tool use and civilization were not present. The Devonian through Carboniferous, roughly 420 to 300 million years ago, saw the colonization of land by vertebrates, the evolution of amphibians and early reptiles, and extensive forests. This period and everything after it represents the time window where complex land animals with potentially sufficient intelligence and anatomy existed. Within this 300 million year window, certain periods are better sampled and understood than others. The past 66 million years since the dinosaur extinction are relatively well studied. The Mesozoic era from 252 to 66 million years ago is also well characterized. Earlier periods become progressively less well documented as rocks are destroyed or metamorphosed. The resolution of the geological record degrades as we look further back in time, creating a detection horizon beyond which evidence becomes increasingly difficult to interpret. Rocks older than about 200 million years have often been subjected to metamorphism, where heat and pressure alter their mineralogy and erase original structures and chemical signatures. Sedimentary rocks that preserve fine details and chemical gradients are progressively rare in older strata. The oldest well-preserved sedimentary sequences come from cratonic regions, the stable interiors of continents that have avoided major tectonic disturbance. Even in these regions, gaps exist where erosion removed material or deposition never occurred. The practical implication is that if ancient civilizations existed more than 200 million years ago, detecting them becomes exponentially more difficult. The evidence would need to be extraordinarily robust to survive metamorphism and tectonic reworking, or it would need to be preserved in the rare locations where ancient sediments remain unaltered. This creates a detection bias that favors finding evidence of more recent civilizations over older ones. If civilizations arose randomly throughout the past 300 million years, we would be far more likely to find evidence from the past 50 million years than from earlier periods, simply because the geological record is better preserved for recent times. This bias must be accounted for when interpreting negative results. Failure to find evidence from the Triassic period does not mean no civilizations existed then. It might simply mean the evidence has been destroyed. Conversely, if we thoroughly search well-preserved sediments from the past 50 million years and find nothing, that provides stronger constraint on the probability of civilizations existing during that interval. The strategic implication is that searches should prioritize young, well-preserved sediments first to maximize the chance of detection, then expand to older and more altered rocks if initial searches prove negative. The interaction between civilization duration and detectability creates interesting scenarios. A civilization that existed for only 10,000 years would leave minimal trace even in ideal preservation conditions, because 10,000 years compresses to a millimeter or less in typical sediment accumulation rates. The chemical signatures would be present but highly concentrated in a thin layer that might be missed by standard sampling intervals. Sediment cores are typically analysed at intervals of centimetres or tens of centimetres, so a millimetre-thick anomaly could easily fall between sample points and go undetected. High-resolution sampling at millimetre or sub-millimetre intervals is possible but expensive and time-consuming, so it is only done when there is specific reason to expect fine-scale structure. This means short-duration civilizations require either fortuitous sampling that happens to hit the anomalous layer, or prior indication that high-resolution analysis is warranted in particular intervals. Again, this creates detection bias favouring longer-duration civilizations that produce thicker anomalous layers less likely to be missed by standard sampling. Conversely, a very long-duration civilization might leave signatures that are so diffuse and variable that they do not stand out clearly against background noise. If an industrial civilization persisted for 10 million years, slowly expanding and contracting, going through multiple technological phases with varying environmental impacts, The resulting signal in the geological record would be complex and might not show the sharp anomalies we expect. It might look like an extended period of elevated but fluctuating carbon emissions, metal concentrations that vary erratically, and organic compounds that appear sporadically. Natural processes also produce complex variable signals, so distinguishing a long variable civilization from natural variability becomes challenging. The sweet spot for detectability might be civilizations that lasted hundreds of thousands to a few million years, long enough to create substantial deposits that are unlikely to be missed by sampling, but short enough that the signal remains coherent and rises clearly above background. This is, perhaps not coincidentally, similar to the duration of many geological epochs and the timescale over which major climate transitions occur. The possibility of multiple sequential civilizations on Earth introduces additional complexity. If civilizations arose every 50 million years on average, and each lasted 1 million years, we would expect perhaps 4 to 6 civilizations over the past 300 million years. Each would leave its own set of signatures in different geological layers. Distinguishing multiple discrete events from continuous natural variability or from measurement noise requires sufficient temporal resolution and adequate sampling. If the civilizations were widely separated in time, they would appear as distinct anomalies in different strata and could be recognized individually. If they overlapped in time or were closely spaced, their signatures might blend together in ways that are difficult to disentangle, especially given the temporal uncertainty in dating methods. This scenario makes the detection problem considerably more complicated because you cannot simply look for a single anomalous layer, but must search for patterns that might indicate multiple events across the entire stratigraphic column. The chemical evolution of Earth's atmosphere and oceans over geological time affects what signatures would be preserved from different periods. Oxygen levels in the atmosphere have varied substantially. During the Carboniferous period, roughly 300 million years ago, oxygen levels reached 35% compared to today's 21%, supporting giant insects and other arthropods that could not survive in current atmospheric composition. Higher oxygen levels affect combustion, corrosion rates, and organic matter preservation. An industrial civilization operating in a high oxygen atmosphere might burn fossil fuels differently and leave different chemical signatures than a civilization in a lower oxygen atmosphere. Ocean chemistry has similarly varied, with periods of higher and lower pH, different nutrient distributions, and varying oxygen content in deep waters. These variations affect how industrial pollutants would be dispersed, transformed, and preserved in marine sediments. A complete analysis would need to account for the specific environmental conditions during each time period when assessing what signatures to expect and how they would be preserved. The role of biological evolution in creating or destroying evidence deserves attention. Modern ecosystems include bacteria and fungi that have evolved to break down many organic compounds, including some synthetic materials. Bacteria capable of metabolizing nylon, a completely artificial polymer invented in the 20th century, have been discovered. This demonstrates that microbial evolution can occur rapidly enough to develop pathways for degrading novel compounds within decades. If ancient civilizations produced synthetic materials, subsequent microbial evolution over millions of years would almost certainly produce organisms capable of metabolizing those materials, removing them from the environment. However, the metabolic byproducts might still be detectable if they are stable and distinctive. Additionally, some synthetic compounds might be inherently resistant to biological degradation, regardless of evolutionary time, persisting indefinitely until geological processes destroy them. Identifying which compounds fall into this category requires detailed understanding of biochemistry and metabolic pathways, areas where much remains to be discovered. The Great Filter hypothesis provides the conceptual framework that elevates this question from historical curiosity to urgent practical concern. Proposed by economist Robin Hanson, the Great Filter suggests that at least one step in the progression from prebiotic chemistry to galaxy-spanning civilization must be extraordinarily improbable. This improbability explains why we see no evidence of alien civilizations despite the apparent abundance of potentially habitable planets and the immense age of the galaxy. If civilizations were common and long-lived, they should be everywhere, yet we observe cosmic silence. The filter must therefore make civilizations either extremely rare or extremely short-lived. The critical question is where in the developmental sequence this filter operates. If it lies behind us, in steps like the origin of life, the evolution of complex cells, or the emergence of intelligence, then we are fortunate to have passed it, and our future prospects are relatively good. If it lies ahead, in challenges associated with industrial technology, resource management, or existential risks, then our situation is precarious. Evidence of ancient civilizations on Earth would strongly suggest the filter lies ahead. If Earth has produced technological civilizations multiple times, then the early steps from chemistry to intelligence cannot be the primary filter, since they have occurred repeatedly on a single planet. But the absence of surviving ancient civilizations would indicate that something prevents industrial societies from persisting indefinitely. Each civilization would have reached roughly our current stage of development, then encountered some obstacle or failure mode that led to collapse or extinction. We would be facing the same filter that defeated our predecessors, with no guarantee of a different outcome unless we can identify what went wrong and implement better solutions. This scenario is deeply sobering because it suggests the challenges ahead are not merely difficult, but potentially insurmountable, having defeated every previous attempt. It transforms existential risk from a theoretical possibility to a proven pattern. The alternative possibility that no filter exists and civilizations simply choose not to expand or broadcast presents a different puzzle. Perhaps advanced civilizations deliberately limit their impact, living sustainably within their local environment without expanding across the galaxy. Perhaps they transition to substrates or dimensions we cannot detect, moving beyond physical presence in normal space-time. Perhaps communication across interstellar distances is more difficult or less interesting than we imagine, and civilizations focus inward rather than outward. These scenarios are consistent with the absence of detected alien civilizations, but do not explain why Earth would have no surviving ancient civilizations if they achieved sustainability. A civilization that learned to live in equilibrium with its environment could persist for hundreds of millions of years, fundamentally altering Earth's current ecology and preventing or dominating our own emergence. The fact that we exist and observe no other technological civilization sharing the planet suggests that previous civilizations, if any, did not achieve indefinite sustainability, but rather collapsed after a finite duration. The timescales involved create psychological distance that may hinder appropriate response. Millions of years separate us from any hypothetical ancient civilizations. This distance makes them feel abstract and disconnected from current concerns. But the underlying pattern, if it exists, operates on timescales relevant to us. A civilization that collapses within 10,000 years of developing industrial technology would seem short-lived from a geological perspective, but represents a time frame highly relevant to contemporary policy. We are roughly 200 years into industrial development. If the typical duration from industrialization to collapse is 10,000 years, we are in the early phase with much of the trajectory still ahead. If the typical duration is only 1,000 years, we may already be approaching critical transition points. Understanding what determines civilization duration is not an abstract historical question, but an immediate practical one that affects decisions being made now about energy systems, resource extraction, environmental protection, and technological development. The concept of civilization itself requires examination. We tend to think of civilization as a discrete state. Either a species has civilization or it does not. But civilization exists on a continuum from small-scale agriculture and permanent settlements through organized states with writing and specialization, to industrial societies with fossil fuel energy and global trade networks. An ancient species might have reached various points along this continuum without necessarily achieving full industrialization. They might have developed sophisticated pre-industrial technology using renewable energy, built cities and monuments that have since eroded away, and maintained population densities and social complexity comparable to historical human civilizations. Such societies would leave different signatures than industrial civilizations: less dramatic carbon emissions, minimal synthetic materials, but potentially significant agricultural impacts, deforestation, and hydrological modifications. Agricultural impacts on landscapes can persist for surprising durations. Terracing, irrigation systems, and soil modifications create features that affect water flow and erosion patterns for thousands of years after abandonment. The famous Angkor Wat complex in Cambodia, abandoned roughly 600 years ago, is still clearly visible in modern satellite imagery, despite being overgrown by forest. Mayan cities in Central America, abandoned over 1,000 years ago, create detectable patterns in vegetation and soil chemistry that can be identified from remote sensing. These are relatively recent examples, but they demonstrate that landscape modifications from agriculture and settlement leave traces. Extending this to millions of years, most such features would be erased by erosion and geological change, but in certain protected environments or fortuitous geological circumstances, some evidence might persist. Ancient agricultural terraces that were subsequently buried by sediment might show up as anomalous layering in exposures or drill cores. Irrigation canals that were filled in might create linear zones of different permeability or chemical composition. These would be extremely subtle and easy to miss, but they represent another category of evidence that has not been systematically sought. The question ultimately reduces to probability assessment given limited information. We must estimate the likelihood that ancient civilizations existed based on theoretical considerations about intelligence evolution, empirical constraints from the geological record, and the absence or presence of specific signatures. This is a Bayesian problem where we start with a prior probability based on our understanding of evolution and planetary history, then update that probability as evidence accumulates or fails to accumulate. Different individuals will assign different prior probabilities based on their assessment of how likely intelligence and technology are to evolve. Someone who views human intelligence as the inevitable result of evolutionary pressures toward greater cognitive capability will assign a higher prior to ancient civilizations than someone who views human intelligence as a rare accident, dependent on unlikely contingencies. Similarly, estimates of how well industrial signatures would be preserved in the geological record affect how much weight to give to negative findings. Someone who believes signatures would be obvious and unmissable will update strongly toward skepticism when nothing is found. Someone who believes signatures would be subtle and easily overlooked will update more modestly.